All right, humans. So live stream is pro. Okay, it is already started. It's been 4 seconds. So let's get started. All right. So where are we? We have. Oh yeah, I was doing array versus linked list.
All right, so we're gonna keep.
And of course, I need to get some watch time. Oh, sorry, I need to read the comments. So let me just copy this URL and let me open this damn thing real quick. So this is muted. Perfect. Yo, medicals, what is up? How are you so fast, man? What are you doing? All right, let me get started. Bam. So we are doing arrays versus linked list. Let's see what is up.
And this is the part of the list, or a part of the class where we're going to do a little bit of comparing
Mm-hmm.
and contrasting. So let's.
Okay. Honey,
All right, so we're going to keep on going.
something happened, but okay.
Fast, right? You're able to just set any value. Something that's really nice about an array is
Yeah.
indice accessing, right?
Yeah, yeah, yeah.
Zero,
That's
one,
perfect.
two, it's fast, right? You're able to just set any value. The understanding of what is actually happening underneath the hood is also pretty straightforward, right? You just allocate the memory however you do it, and then you can just access that and you set those values.
Yeah,
The memory is
totally.
understood based on the type that you have cast it to. There you go. Very, very simple. Obviously, some of the problems with
YouTube gave you a notification fast today. Okay, that's good. So YouTube is doing its work. That's very good to know.
Insert.
That's very good to see.
And so that causes problems. You can't really insert a value into an array without actually writing the for loops manually to shift everything over, then put in your value, or unshift everything and write over your value if you were to delete. And so it does cause it to be a bit more difficult. Time-wise, arrays are really, really nice. It's O of 1 everything, right? If you want to write over a value, it's O of 1.
Okay.
If you want to get a value, it's O of 1. It's fantastic. But, again, there's a bit of a problem just with the usability of it all. So I did want to kind of point this out, which is interesting. So one thing that's unique about an array is that you obviously allocate this all up front, meaning that if you wanted the potentials worth the if you do allocate, or if you create a list, memory usage is more optimized, but there is a difference of runtime cost there, right? With an array, the memory has already been retrieved. It is already there, so you can easily use what you have. So
yeah, that's totally fine.
The constant C that is there just is smaller. Now you could obviously create some sort of object pool, hold on to old deleted nodes so that way you're not creating a bunch of new ones, ways to speed up a list, but still you are creating a containing node, you're setting up links. It's a little bit more cumbersome than say an array.
What this cumbersome means? Thinking of learning modern C++ for making VST. I don't know what VST means. I know DAW, the audio workspace thing. VST. So let's see. Virtual Studio Technology. Okay, something audio related. Okay. What do you mean by modern C++? Like, do C++ have a new syntax now? Modern C++ versus C++. The phrase term is not a brand specific standard or kind flavor of C++, and it means a C++ compiler. Okay, so pretty much new version of C++, which is active since probably few years or something. Okay. So kind of like Node.js 16 or Node.js 18 is latest now, something like that, I guess. I don't really know much about it, so looking forward to your comments.
That's nice about an array or a linked list, though, is just always will use less memory.
Yeah, totally.
But the usability of a list is a little bit different, right? If you wanted to get an item out of a list, you have to traverse.
Yeah, that's a pain, man. That's a pain.
Until you find it, so it's like always a linear search. There is no such thing as a binary search on a linked list. You can't hop into the middle. You have to walk the whole thing. So linear search is really your only option on a linked list, which does make it a bit unfortunate of a data structure when it comes to that type of operation. So typically, if you need to scan a list or hop into a list, do random access,
then array is better.
More like an array.
If
you want to be able to just push and pop from either the head or the tail, you tend to want to be able to use something like a list. There's a trade-off. There's an intentional trade-off you should make when deciding this. So a good example of this is, say, like an async request queue. Say on your front end, you don't want to have more than 5 network operations happening at one point. For whatever reason, you've decided this is the case.
Okay.
So then you're going to have these promises that are generated, they go off, but you only want 5 of them active at any one point. That means you're going to have to pull off the front and you're going to have to push onto the back as new ones come in and as old ones complete. So you have this whole problem of a queue, but you don't want to be using an array if it's a really highly used one, because now you're shifting all these indices around using a JavaScript array. It's not going to perform very, very good. It seems like it's a bad idea. So it's good to know what you have and when you want to use something. Always play that over in your head. Is there any questions on usability of these two? Maybe in JavaScript land it's a little bit less apparent just because it's just you just have brackets.
How would you traverse a linked list, or would you just not even try that?
So how would you traverse a linked list? Here, I'm going to go back to the code, and we'll just, oopsies, I'm going to go back to the code, and let's go to doubly linked list. So if I were to create this thing, right, I'm just going to go fast. You don't have to follow along on this one. Let's just pretend we have this beautiful thing right here that has...
Okay, so I will make my doubly linked list as well. Why? Because he's making it, so why don't I try as well? Let's do it. So I will start with copying this beautiful node, then I will try to find the doubly linked list class. And I'm in the wrong folder, my apologies. Let me go to the beautiful doubly linked list. Yeah, there it is. So first of all, in the next section, we also need a previous section. I will do prev. Now we have length. I will say that let's keep head and tail as well. Where do we have our linked list? Singly linked list, there it is. I have not made a singly linked list yet. I'm dumb. I think just head is enough, to be honest. I mean, we can have tail as well. It's totally on us. Like, do you want it? You have it. You don't want it? You don't have it. It's your thing. So I will keep both of these. Let me also copy this constructor because it's same. Why do I have to rewrite this? All right, paste. So we have our length, we have our head and tail. In the constructor, all of this is undefined, length is 0. Now prepend, I don't really know what that means. I'm assuming it is like insert at the head, most likely, but I will just Google search it. What are you doing /learning? So I am like, there is, you know about data structures, DSA. So I know some of these thanks to my school, but I don't really know. Like, there are a few things which I don't know here, like quick sort. I have never tried that. I don't know a lot about trees, so I can give that a shot. And I don't know much about heaps and graphs, at least. And I don't know much about LRU. I probably know about maps. So it is pretty much like a good revision and good learning. I don't know, man. I'm just, if I'm being honest, then I was just bored, so I didn't know what to do. So yeah, add something to the beginning of something else. All right, so prepend means add something to the head. And how do we do that? That's a good question. How do I prepend something? That's very interesting. So if, first of all, I would like to make a child. So child will be as node, it will be a node. So what do we need in a node? Let me also select a type, my bad. All right. So in a node, we need a value that will be that. And after that, we will need next and previous. All right. Do we worry about that? Why not? So we are adding, so we don't need a previous one. And for next, we can just do this dot head. Simple. All right. Now, if we do not have this dot head, that means the list is empty. In that case, we simply do this dot head is equals to this dot tail, which is equals to this child. Because if child is the only thing, then it is the head and tail, blah, blah, blah. If that is not the case, that means else. Now in the else condition, what I can simply do is, first of all, I will do this dot head dot prev. Sorry, what? Object is possibly undefined. Are you dumb? Okay, not a problem. All right. So what's your problem now, sir? Is this thing dumb? Why is it not giving me suggestions? This dot head is never. Oh, I'm supposed to add this. My apologies, humans. I'm really sorry for that. So this dot head dot prev, that is previous, is equals to child. So this means what I'm doing is I'm setting something as the previous element of the current head. That means the current head will be equals to the children. Right. So this thing already have it in the next, blah, blah, blah. This should do the trick. Trust me. You can totally trust me on this. Now insert at is going to be a pain, so I will ignore that for now. Append, I'm assuming remove the last one. What the hell is killing your mind today? It is DSA again. I'm going to do some DSA stuff. So append means add something to the end. Oh, my apologies. We have to add something at the end. So what I will do here is, first of all, let me go to my processes and let me find something very interesting. Okay, I was unable to find it so far. Why the hell I have Microsoft Teams? I don't even remember installing that. That's a virus. Why the hell I have McAfee? I don't even remember installing that. I totally remember uninstalling that, to be honest, but can't help it. My bad. Now in the append, I will start with copying this code. So if we do not have a head, that means we do not have a tail. So it is the same thing. This part can stay the same. But otherwise, what we will do is this dot tail dot next. I will do this dot. Oh, all right. So this dot tail dot next is equals to the child, and this dot tail is equals to the child. And here we will have previous is equals to this dot tail. Trust me, this will also work. I mean, if that doesn't work, then I will need to redo it. Got your IP. That's quite tragic. Please don't do something bad. And let's get back to Control Shift ESC. Yeah, I was trying to do something here. Let's see. Power noise, color picker. Okay. Let's focus on linked list again. My bad. So if we want to remove a element, then we want to get an element, then we want to remove add an element. Okay, these things are doable. I will start with get because get is really easy. So how do I do the get? So first of all, I will do let current element is equals to this dot head. Then I will do current index is equals to 0. All right. Now I will run a while loop. Okay. While we have current element question mark dot next. All right. I don't really remember why I added 2 brackets. Oh yeah, that is because of Java. In Java, I remember adding something like is equals to null. Ignore that, guys. That is Java. That is bullshit. Okay. Anyways, so first of all, I need to make sure that I have something to check. Like this thing is not ended. The linked list is not ended. And secondly, I also need to make sure that the current index is less than the IDX. Why? Because if it is equals to the IDX, that means we are already at the element. Congratulations. So while this loop is running, first of all, what we do is current element is equals to current element dot next. Then what we do is current index plus plus. Now here what I'm going to do is return. So if the current index is equals to IDX, right? IDX, that means congratulations, current element dot value. Otherwise, okay, I will also do and current element exists. Okay. Sorry, it is supposed to be current index. What the hell? Otherwise, we are going to return undefined. Okay, looks perfect. What is T? Item T. I guess I don't need to return the value, I need to return the item, right? Is that the case? What's your problem, son? No T or undefined is not assignable to type T or undefined. Dot value. Brother, this thing is weird. Okay. So as you can see, the get function is ready. Of course, I have not tested it, but I trust myself. Now we need to remove something that is painful, man. So first of all, remove function is boring. Okay, I will just this is so painful. Okay, I will start with index inserted. Okay, so first of all, I need to find the child. Then what do I do? Child is equals to a new object. The value is item, and it is a node T. All right. Now I need few more variables. I need the parent, and I also need the child. All right. So a child can be parent for now. All right. I mean, it can be null to be honest. Okay. Let new child. Okay. Then we have current index. So what we are doing is we are checking if the parent dot next exists. I will not define child here. I will define it later. That's fine. Okay. So if the next guy exists and the current index is less than the IDX, then we run the loop. Now, if the current index is not, then we just return. No, then we just edit at the end. That's fine. Perfect. Now here what we are going to do is we will do parent is equals to parent dot next current index plus plus. Now what do we do next? We will do const child is equals to parent dot next. Now what I'm going to do is I will do parent dot next is equals to new child. What if parent does not exist? Oh my goodness. What do I do? That is also simple. If the parent doesn't exist, then I will just return this. Sorry, I will return, and before that I will do this. Of course, I will need to change it to new child. My apologies. I'm not very sure if this is the most um, ideal, best working code, but it works. It better work. So what's the problem here? We don't need question marks. Sir. So parent dot next will be the new child, and new child dot previous and new child dot next. Um, I think I have messed something up, but I will ignore it for now. And next will be the child, and if child exists, then child dot previous will be the new child, and we don't need to return anything. So if things are good, it will work. If things are not good, it will not work. Anyways, why is this thing running? Oh, it is a stream.
As a value t, do that, and that would be our node, right?
Yeah, it will be totally.
I hate that. All right, so we're going to keep on going here, and this is the part of the list, or a part of the class where we're going to do a little bit of comparing and contrasting. So let's think about the usability. So I won't implement all these operations. We'll just do, we'll just do this, right? This dot length equals 0. Why not? Do all that stuff. So if we were to do a, let's just say a get operation on a linked list, well, what do we have to do? We'd have to first go, I has to be less than index, and there has to be something there, right? So in case we try to grab outside of the array, we could do a length check right here if we really wanted to. But again, it just makes it completes Goofy for TypeScript, right? So now that we're here, we can just go current equals current dot next, right? So we literally walk forward one at a time. So there is no simple way to get there. We just literally have to walk it. That is why it's considered a linear operation, because you have to walk. And then at that point, we can just do the old cur value, right? Awesome. We have now successfully just wrote get at a specific index for a linked list. So not too hard, but at the same time, you can see.
Wait, that code looks more beautiful. Hello, Azam, what's up? And I am good. How are you, brother? How are you? Or yes, we can just do question mark dot value, because if it is undefined, then it works. I guess, my bad. Then this part is done. Yeah, it is fine. It is fine. Code is beautiful. Code is beautiful.
Why this is like a very inefficient operation. If you had a big list, that would obviously just destroy performance. So the question is, can we do better? Can we have array access with the ability to grow, right? That's kind of what we want in life, is that it's something that I assume at least we all want that, right? And the answer, of course, is yes. Now remember, I did say with an array, we can write these operations in, right? We can do a for loop and shift everything over or shift it back if we want to delete it. We can do these things. We just have to write these things ourselves. Now in some languages, they just provide it. Like if you think about JavaScript, you actually have a list implementation where you can choose between a linked list and now what is referred to as an array list. It's an array list where instead of having underlying containers, we have an array of generic T, and we can use that, and when we need to grow, we have to grow it. So let me explain how this one works, because it's actually it's a pretty neat idea, and it's also going to be the basis of that is from 0 to 3. And let's just say we're storing numbers, right? It doesn't matter what we're storing. And so we have in here, we have 2, right? That's all we have in here so far. That means we have a length of 1, right? We have 1 item in there, but we have a capacity of 3. Does that make sense? We can store up to 3 numbers, but we have a length of 1. So that means if we were to do a get operation, say a get with an index, well, we could do a couple things. A, we can use our length that we're kind of holding on to, that we're maintaining, as a way to say, hey, you're either accessing in or within or without of our array. So if you exceed this index, so if IDX is greater than or equal to length, well, then we could, throw some sort of error, whatever we want to do, right? So capacity. You're within the capacity, operable O length, or undefined, right? So now you also don't have to zero out the data with primitive structures. If you're using a language that uses pointers, you can technically just, you can still leave them in there because there's nothing that you're actually doing, right? Unless if it's, of course, a shared pointer using something like Rust, blah, blah. There could be all different ways in which you would want to clean this up. But in general, if we're just talking about a simple array underneath the hood, you don't have to clean it up because you are using length to keep track of what you own.
Yes, sir.
And you only clean up as you need to. In Java land, you'd probably want to set it to null, because nulls are you releasing a pointer to an object, thus it can be garbage collected, right? There is some dangers there, but understand your environment and what you're doing and why you'd want. When we exceed capacity, and that way I don't allocate too much memory, and that way you're not using a bunch of empty space, because if it starts off by saying, hey, my initial capacity is 30,000, that could be way too much. It's just wasting a bunch of memory. So it's a game here. There's definitely a game you have to play in which you want to be as, use the least amount of memory, but do the least amount of growing operations.
Okay.
So then pop obviously would act. I've never seen a data structure that actually reduces its capacity once it reaches a certain point. I guess you could if you had to be very, very efficient about memory. Say you're using an extremely low memory device. You could do that, but I've never seen that personally.
Okay.
There we go. That's the effects of an array list. But let's think about it, because we've only covered 2 operations. Push and pop, which are stack-like operations. What about queue-like operations? Q or NQ and DQ. Well, if we were to do that on an array list, if we were to take this and say we had the values 2, 3, and 5 in our underlying array list, well, first, we're going to have to grow our capacity, right? We're not able to actually sustain any further items. So let's say we grow our capacity. Awesome. Our capacity is now 6, right? And so now we can insert at length. Problem here. The problem is actually quite simple. You can't just write. This is an array. If you write, it writes over the value. So what are you going to have to do? You're going to have to start here and go move over 1. Move over 1. Move over 1. Now we have created a spot in that position for you to be able to insert into the array list. And so that's why often you'll see people getting up in arms about using insert into the front of a list, because if it's an array list, you have to do an n-like operation and actually shift over all of your underlying values, and they're very, very not performant. And that's why you see people liking, say, queues with node-based items, because you can do this in an O1 operation, not O-N. So exact same thing with a DQ as well. If you do a DQ, what happens? Well, a DQ, you're going to have to literally shift over every single item, and you can write over, and then you're going to have to shift over this direction, right?
Yes, sir.
And now you've just shifted everything back, or a value you...
Ye kaun hai be just got back from lunch. He is the... Let me just check the name. Prime something. He sounds like a cool smart guy, so checking out his tutorial.
Already cleaned
Or maybe a course, I'm not very sure what category it comes in.
Effectively say that long as you're pushing and popping and you reach some sort of stable state, you're going to have O1 performance pushing and popping. It never has to grow the array. It never has to do anything. It's just very, very, contained in a certain... Everything beyond the 5th index needs to be shifted down. So those are O of N operations.
Okay.
All right. Let's see, did I miss anything? I don't think so. Running time, yep, we talked about all the deletion / insertions. They're the same thing, right? If you insert, you have to shift everything over. If you delete, you have to shift everything over the other direction. They're pretty straightforward. I think I'm going to skip the implementation on this one just because it is, again, a very lengthy implementation, and it's not very hard. You see the for loops you have to do. You go to that index, and you just have to shift over values. It's too hard on this one. There we go. So which one is better, right? Which one would you rather use, an array list or a linked list?
Doesn't it depend on the situation?
Man, it's like you guys know the thing. It should always be it depends, right? It is always it depends. Whenever someone asks you that in an interview, say it depends. It depends on the situation. That's why I always do so terrible. I emotionally do so terrible at Google interviews because they're always like, let's say we're inserting and removing millions of items. And I'm like, well, you don't really, I mean, you're really doing 100 million items on a single machine. Are you really doing this? This already seems so not even feasible. Let's talk about why you're doing that. Like I've already lost the battle. It just seems so fake. But you know, experientially, it depends. If you're pushing and popping from the end, well, either a linked list or an array list can work quite well. You get a little bit more conveniences because often with an array list, you also have like say angle bracket accessing. You can have that with a linked list, but it doesn't often happen. But at the exact same time, you have random access with an array list. Give me index 3. Oh, that's constant time. That's really, really good. But you do not have a remove from the front. So it is definitely a trade-off. There's definitely a trade-off graph somewhere on there that you have to be careful of. Getting sucks on linked lists, removing from the front.
Why I am seeing this? I am bored and I wanted to do something, and that seemed like the most doable thing. I mean, it is pretty nice and easy, so why not, man?
On a rescue,
Come on.
in which only 3 requests can be out at any one time, or 3 async operations can be out at any one time. And when they would inevitably use an array or use the JavaScript brackets, I'd go, why would you not want to use those? And they'd say, oh, well, I'm using them because you can do shift and unshift. And I go, okay, what happens if you have a million items in there? Do you still use them? And they go, yeah, why not? And I know for a fact they haven't thought about the fact that when you remove or add to the front, you are fundamentally having to shift everything. Like I want to hear these words out of their mouth because it is very, very important you understand what you do. Right? I don't care that you don't know how to implement. Who cares you don't know how to implement it? You just have to understand that there is a cost at some point in the system.
Okay. Very sensible.
I know you probably feel like you've had enough lists, but there's still one more list I do want to cover. I think it's a very fantastic list. It's one of my favorite lists. I use it all the time. I tried to make a PR once to an open source library a while back that wasn't using one, and it would just cause terrible performance, and they didn't accept my PR, but I do think I was right on doing it. And of course, that is array buffers. I've created bajillions of these. I've created a bunch of them just this year. It's a very fancy word, but it's not actually all that confusing. So let's go over an array buffer. Oh, I just love them. They're just the best. I believe these are used in, if you're familiar with Rust, vecDQ or dqvec. That's what they are, as a double-ended ring buffer. So effectively, you can think the exact same thing as an array list, right, where you have 0 to n, and you have some sort of array-like storage.
Yes,
the
sir.
only difference is that we're not using 0 as our head and length as our tail. That's what's happening in an array list. You can kind of imagine it kind of like a linked list. Instead, what we're going to have is we can literally have index-based head, and we can have index-based tail. And so they exist somewhere within the list, where you can imagine everything this direction is null, everything this direction is null. And everything within the head and the tail are the items that you have.
Oh, DQ, I remember it now.
So if you wish to remove from the front, what do?
We increase the head.
You just +1 to the head, and now that item that was the head is no longer in there. We clean it up, return it out, and now we have a new one. So that is an O of 1 operation, which is fantastic. Same thing with tail. If you wanted to add to the tail, what would you do? Just add 1 to the tail, right? This is just tail +1. Boom. And now we've updated it. So pushing, popping, shifting, unshifting, all are O of 1 operations, which is fantastic. But I can tell you guys are so astute. I can just see the astuteness. And you're saying, well, checkmate, instructor, what if you go off the edge? Well, that's why they're called ring buffers, people.
Oh, then they will. Yeah, yeah.
Modulo operator, right? So tail, this dot tail modulo length gives you your index into the array, so you can ring around it. So your head can literally be on this side, and your tail can be over here, and you still have the same thing. Now, if you need the resize, that's where things get a little bit confusing, right? Because resize, by the way, is everyone familiar with the modulo operator?
Yes,
The
sir.
modulo operator is the remainder operator. So 5 divided by 2, the answer should be 2. All the, TypeScript rots your brain so much, you're like, 2.5. It's like, no, it's 2, remainder 1, right? So 5 modulo 2 is 1, right? That's the answer. Most languages don't convert from integers to floats without your permission. You need to say, hey, this is now officially a float. You can put a point in there. Fun little story. Anyways, this does the 10, 2. So you can imagine if tail, let's see, if you had a 24, let's just say it's 24, somehow it's bigger than your tail. Don't ask questions, it's just somehow bigger than your tail. 24 modulo 10, of course that's 4. So your head would be here at 4, your tail would be at 2. That means you're using from 4 until 2, right? So that makes sense, right? You can actually go around, it's like a little ring around. The only problem happens is when your tail exceeds your head. Once that happens, A, you're probably falling down some stairs, but B, what actually is happening is that you need to resize. And so this is where a little bit of the tricksiness comes in, because one thing that's inherent about ring buffers is they also maintain order. So when you shift or unshift, you're not just getting any element, you're getting the element that was last added into the front, or perhaps the first element added, right? So if you're only adding to the tail and removing from the front, you're just simply creating a queue, right? That's all you're doing, a queue that runs around a ring. And so you do have to do a little bit of that, and you'll have to resize. And a resize is pretty straightforward. So if you did have this situation in which the tail is now where the head is at, and you're trying to insert, well, all you have to do is start at your head, go the length, and write that into a larger capacity buffer, and there you go. You now have it rewritten in proper order. Your tail or your head, or let's see, what your tail would be at 0. Now, your head would be at 0, your tail would be at length, and there you go. Now you can just add one because you have more capacity. Everything's good to go. So ring buffers are really fantastic items. Hopefully, this is just an explanation point. We're not actually going to implement them, but they are a really great list.
Why not? Do we have a file for that? It's in the okay, we don't have it.
To know you have, because inevitably what's going to happen is you're going to write something like, let's say a log
Do we have
batch,
DQ?
right? You have a service in which needs to batch logs and then write
Okay, so why don't I make a DQ?
logs.
I don't.
The problem is logs need to maintain order, and while you're writing logs, new logs can come in. So you can imagine something that doesn't want to take too long writing logs, doesn't want to do this. You could use something like a ring buffer in which every so timer, it flushes 50 logs, 100 logs, some amount of logs, all the logs. You don't really care, you just flush it, and then you have something that can keep on running while it's doing it. And you don't even have to worry about putting, say, a mutex around it. I know this is like maybe a little too unsafe for all the Rustaceans out there, because you don't write into memory that's being used until your tail or your tail exceeds your head. So you have this like free space. You can do some really cool operations with it. You can make it super duper fast, where you don't have to worry about some of these read-write operations. You don't actually do something that's bad. Oh, we got one question.
Is it called a rain buffer?
A ring buffer. A ring buffer. They're a lot of fun, and you can use them quite a bit for performance, object pooling. If you really want to use a ring buffer for object pooling, you can just use an array list for object pooling, because often objects don't need to be they don't really care if they're created the last or added to the pool last. It's just like, I just need a new object to reuse again, and so you don't have to do that. For those that don't know what an object pool is, say you have a service that creates a user every single time a request comes in. You're getting thousands upon thousands upon thousands of requests. Why recreate this object over and over and over and over again? Just have an object, set new values on it, use it for the service, hand it back to a pool. So that way your memory doesn't go like this, instead it goes like that. Just makes life a little bit easier. And often you can run into situations where you don't get garbage collection destroying your... All right, so now we're going to reach the point, kind of the culmination of this entire section. Let's do the empirical testing for what are we using in JavaScript. We're going to find out now what is those brackets in JavaScript. Is part 1. Frustrating? Could be. No guesses?
Array
Array list, great guess. I will tell you if you're right or wrong, because we're gonna find out empirically. So I did write this little, I didn't know where to put it, so I just put it right in this kata thing, so you can even follow along if you want to. All we're gonna do here is we're gonna simply create an array, right? It's just a number array. I'm gonna be able to measure a function. We're measuring in milliseconds, we don't really care, it's not super precise. We just wanna get a gauge of how fast or how slow these things are, right? So no hardcore testing here. So I create a function that simply will unshift a certain amount of times, right? Unshift in JavaScript, remember, that's adding to a list. Thank you, Brendan, for that one. Shift, just push, pop, shift, unshift a number amount of times. Lastly, we're gonna have get based on index, so just in case it is a linked list underneath the hood, if we were to get progressively larger indices, we should see a slowdown that keeps on, we should see a linear slowdown, right? So then I create this thing, just some little, some higher order function nonsense. I can push it, I can create something that will just have the same function that calls push with the same count every time, right? So I can call it over and over again. I don't even know why I did it this way, but it just feels like it was a great way to do things at the time. I can't even remember what code comes down below. Lastly, we're gonna test with 10 elements, 100 elements, 1,000, 10,000, 100,000, a million. Whenever you're doing performance testing, a little tip is you should always do a stepladder type approach. That way you can see how it grows. You can really actually run, like, say, a linear regression and say, hey, this is kind of more what I'm seeing right here. It's not it doesn't always work exactly, right? So there you go. So you can see for every test I'm gonna do, I'm gonna push in the value, and then I'm going to do a get at the last element. So if indexing is linear, we should see a slowdown as the array gets bigger, correct? Correct, right? It should be 10x slower effectively every single 10x times some constant. Pushing, exact same thing. We're gonna push 1,000 items after growing it to a certain length. So first we're gonna grow it to 10, we're gonna grow it to 100, we're gonna grow it to 1,000, 10,000, 100,000, a million, 10 million, and then at each one of those points push in 1,000 items. If push is based on the amount of items within the array, we should theoretically see a slowdown that happens, right? It should be linearly increase the size of our array by a factor of 10. We should see a great, let's do this, source, I did it in TypeScript, npx ts node. So what do we see here? Well, notice that get really didn't matter the size of the array, right? It was always super duper fast. Push didn't really matter. Pop didn't really matter. Unshift, you'll notice it just got really, so we're not even done yet.
Is it a linked
list? It just
list?
got horribly slow at some point. And so what are we seeing here? Well,
Maybe a mixture of linked list and array list.
Time operations. And there we go. Awesome. And we're seeing shift and unshift grow. It actually looks like it's effectively a 30x growth or something like that, but we'd call that a linear growth. I would call that a linear growth at that point. 10x the array, something like 10x the time it took to run. And so let's just write that out. So if get unshift, we're saying instant access, we're saying instant pushing and popping at the end, we're seeing linear shifting and unshifting, or in QDQ. And a reason, of course, we can now reason in our head the exact reason why. Underneath the hood, what is happening? 0 to n. You're
Looks
shifting
like we are
over
linked.
n elements, however that many is. I had 10 million at one point. That should take a long time. If I had to do that 1,000 times, you can see it took multiple seconds on my computer just to execute. That's a real problem, right? Right. So hopefully this was.
Sorry, that is an array list, because array list need to shift everything. Linked list we don't need to shift it.
I was really hoping.
In linked list, the get thing will be slower.
Hoping that this would kind of culminate in a cool moment where we really
It is an array
understand
list for
all
sure.
the different types of lists there are, and then we can empirically look at something in which that. What happened if I told you const A is not an array? Yes, Morpheus, the answer is it is definitely not, and it is an array list. Awesome. I hope everyone's awesome. I always was very curious why they didn't use a double-ended ring buffer. I'm sure there's a great reason why. I just don't know why, but I'm sure there's a great reason why that doesn't happen. All right, is there any questions at this point? Because I feel like it's a good, I think the next slide is actually, yeah, anything unclear? We're kind of ending the list section. Oh, sorry, let me rephrase the question. Shift and unshift was exponential. No, it was linear. Sorry, keep going with the question, just so.
It's a linear, right? The shift and shift, okay.
It's linear.
So what's the conclusion? The question was that an array or not, right?
Yeah, was it an array or not? It's not an array because it's growable. You can push and pop. It actually has a notion of an ending and a beginning. Those are all very, very different from what you would get with an array. An array does not have these, and the kicker obviously is this right here. So for those that don't know, he asked if it's not an array, what is it? It's an array list because we do get all these sweet He might be trying to say splice. That might be the confusion here, or an array list.
What about slice?
Slice, well, slice is just a copy, right? He might be trying to say splice. That might be the confusion here. So slice is effectively when you do a slice on an array, and you're doing it from, say, I to J, you're just saying, like, I want a copy from here to here, right? Starting at I up into but not including J. So that's effectively just like a mem copy, right? So that's a linear operation. All it's going to do is just take that amount of memory, copy it to a new location, hand it to you. There you go. And so if you're using an array list underneath the hood, you could effectively copy that. You could create a copy method, right? Hey, create a new array, copy all my elements in, and then take all my state, and there you go. We have two lists, two separate copies, and now you can 100,000 subs. Oh my goodness. No, anyways, it depends on what you mean by a copy. Equals 5, A1 equals 5, A2 equals 69 for the memes. There we go. We've appropriately done all the meming. There we go. So now if we do this and we go const b equals a dot slice, say 0 to 5, and I go b3 equals 5, if I look back at a, notice that 3 is not 5. We have done a deep copy of the data. Does that make sense? Now, here's where things get great. Here's the best part about it, though. Instance of uint8 array. It is a uint8 array. So by even TypeScript definition, it's a uint8 array, correct? Now we can go like this. Buff dot, I think it's set. Let's see, what is it? Oh my goodness, what are you? Is it right? I always forget these things off the top of my head. What are you? There we go. Write uint 8. There we go. Let's write uint8 at position 0, 5. And then it's going to say this. Hey, the value offset range, blah, 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 blah. Oh, I had it backwards, of course. Write value 5, offset 0. You know, Node has always managed to be backwards on all the APIs, I swear. If we write out buffer right now, you'll see it has 5 in that first position. Awesome.
Sure.
So let's do the exact same experiment. Const buff2 equals buff slice 0 to 5. And go buff2, right, buff1 was. So this is actually a shallow slice. So buffers in Node are shallow sliced, meaning that they just simply have offsets within this contiguous memory space in which they're actually just saying, hey, I exist between these two places. And so when you say, hey, give me a slice, I just simply adjust the indices and then still point to the same piece of memory underneath the hood. Now, obviously, the danger, of course, is where I showed you the whole, where are you? Where did I do that? The instance of, right? Wherever that was. I don't even know where that was. But it, for your APIs, looks like a uint8 array, but it's a buffer. So if you call slice, you're getting a shallow slice, which means you could mutate data. You think you're not mutating. So very, very dangerous. Very, very node-like. All right, there you go. So hopefully that makes sense. Slice, it can be linear if it's copy. It obviously can be constant if it's literally just pointing to new spots. Out the array buffer that's backing the buffer underneath the hood, we'd actually probably see a much larger one. We might even see source code and other stuff like that inside the array buffer. Yeah?
Just a general comment. I've seen quite a few people asking, like, where would I apply this in my code, or what are some typical examples that you've run into? For instance, you said you use, X data structure quite often. So
where would I actually use these data structures? I've said that I've used them, so where would you use them? I did give the example of, like, say, if you're doing any sort of log or flushing. So flushing in general, things in which you batch operations and then want to release a bunch of operations, you're using some sort of data structure underneath the hood, and you're going to want to be efficient with it, right? You don't want something that has a linear add or remove time if you're not flushing the entire thing. So you can imagine that could be really bad for a service. You tend to run into these things a lot more on the back end than you do the front end. You tend to run into them on the front end when you're writing a library. So if you look at, I'm sure, the React code, if you look at any code, I am positive you will see data structures just around because they're trying to keep track of a bunch of state and they're trying to be as efficient.
Crazy developer, no voice. I was just kind of sleeping. Let me just get back. Okay.
Possible. So they need to know all these different things. They need to do that. So I tend to run into it a bunch in library development. When I did a caching layer at Netflix for the TV, for JavaScript, I did a bunch of trees, linked lists, and maps. Right? You just have to be able to do all these things because that's what you just had to be able to do those. Because at that point we have to be as efficient as possible. Everything needs to be OV1 if possible. We cannot interrupt the UI. And so that was just a part of it. And it's a very, very interesting kind of concept. So that's where I tend to run into it is more backend or library dev. Never really, like if you're just writing a UI component, often you're not actually doing logic. You're just kind of like displaying logic, or you have very limited interaction with logic. And so therefore it tends to be a little bit more shallow on those.
When you're dealing with big data, what is your go-to?
So I don't deal much with big data. I'm not the best person to answer that one. I use Hive. Hive does a bunch of really sweet things. Okay. And so, and my Hive experience is like select star from, you know.
Oh, okay. So it's just.
And then I eventually write some joins. It can't compile. Then I go to my data scientist friend and go, help me, please. I'm poor in Hive, help. And then they help me, and then I get answers. And so that's what I usually do at Netflix, at least. So, but big data are often applications of these principles over, say, a map and reduce. You have consistent hashes. You have to map things to specific computers so that way you can run medians fast, blah, 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 blah. Like they're all applications of these algorithms but ran distributively. And that obviously is much harder. Kafka is just a queue, but it's like a much more complicated queue. And so now that you fundamentally understand what a queue does, you can imagine what Kafka does, except for you have to somehow solve this whole in-order, async, multiple computer problem, right? So it's just a distributed queue. And so it does help you visualize what's actually happening on the other side. Moral of the story, don't use regexes. All right, I think we should probably continue on from here. Regexes are just graphs underneath the hood, and traversing is the characters in which go through that. So there you go. Graphs are literally there. All right.
So I have a feeling that there is a cut here. Something is missing. What is this resource download button? I don't know about that. So that is done. Bookmark layout. Table of content. Yes, course, exercise, transfer.
So we're kind of getting into the next part of recursion. If you don't understand recursion, you can always Google it. Though I did find a bug in recursion. Are you ready for this? So if you don't get the joke, if you type in recursion and you hit enter, Google will say, did you mean recursion? And oh my goodness, I can't see my mouse due to 4K. And if you click it, it'll say, do you mean recursion? And you keep on asking, it does it forever. That's like the joke,
that's
right?
the joke.
But if you misspell it and it says search results for recursion, it actually doesn't do the recursion joke. Look at that, I busted Google. Anyways, I thought that was kind of funny. I discovered it like 2 days ago.
That kind of was.
So, because I mistyped recursion. Anyway, so that is like the most visual way you can look at recursion. It's something that keeps on calling itself over and over again. In this room, how many of you are familiar with recursion?
I.
Okay, we got a couple no's, a couple yeses. I even had a hand back from the production staff. I was like, oh, I got it. That was awesome. How about Twitch chat? All the chats, front-end masters chat, how are they? Pretty good. 1 if you don't know recursion, 2 if you know it. Because I'm just curious how much...
He should have used 0 1. That will be better.
Like the average understanding of it is.
I would say it's split.
Split? Okay. Recursion is one of these topics where you literally just... It's super hard.
Definitely more 2s than 1s, but
okay.
There are quite a few 1s.
So we're gonna go over it either way. Even if everyone in here understood it, someone doesn't understand it. Recursion was my personal hardest one.
Even have a 1.5.
1.5? 1.5? Really? I've met very few 1.5 understanders, right? Because either you get it or you don't get it is how I've generally kind of found it. So the simplest way is a function that calls itself. And this keeps happening until it reaches something known as a base case. At that point, the function no longer calls itself, and it's able to return out some value or do some operation or do something.
Interesting. All right.
thing, right? And so that depends on what you're doing with recursion. With async, I found it to be extremely difficult. And so we're going to go over two things with recursion. And what I'm hoping is that by the end of this, you'll feel very natural with recursion. You'll feel like, okay, this actually isn't all that hard. It's hard. So we're just going to do it. So the simplest form of recursion is this right here. You would know this as like a sum, right? So if I said sum the numbers between 0 or from 1 to 100, you'd be like Gauss and say, well, and I'd say, no, sum it. And that's what we do. And so this would be an example of summing it. What's exactly happening here, we're going to also write out everything that's happening here. But you can see I have a function foo that takes in a number. The base case, of course, is when we're equal to 1, the sum of 1 is 1, right? We know it. We could technically extend the base case for as long as we know the sums, but this is just the generally easiest way to think of it. So when the number is not 1, we are going to add the number itself plus recall foo with 1 less than its current number. So it would be 5 to 4 to 3 to 2 to 1, and there we go. Now, we're going to draw what's happening here because there is this whole problem. Now, one thing I really did want to highlight, I'm going to say this like 5 more times. I'm positive I have it in my slides like 5 more times, but base case is extremely important. Always think clearly what your base case is. If you don't know your base case, recursion is extremely hard. If you know your base case and you can make it clever, recursion becomes exceptionally simple. So good how it works. So return happening. There is scouted more traditional languages. They compile a lot of these things in. There's a lot of sweet oppos too. It needs to code really about function calling. There's 3 values you can kind of really help to visualize this. There is something called a return address. Every single time a function is called, it needs to know how it got here, right? Because when the function's done, it needs to literally go back and hand back out its value, right? And so it needs to know where that value goes to. Another important part, of course, is the actual return value, right? I need a value that I could return. Now, in more traditional languages, they compile a lot of these things in. There's a lot of sweet optimizations, blah, 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 blah. But what matters is that they have to make kind of a space for it, right? And then lastly, we have our arguments, right? That makes sense.
Okay, let me mute myself. Yo, Warman, what is up? What is up? Wait a second. Okay. Let's get back to work.
Into the function. So every time you call a function, this is kind of roughly some memory that is put into your system, we'll say. So when I call foo5, what happens? Well, our return address is whoever called foo5, right? No, we know that it's 5 plus foo5. What does it do? Well, let's look at the code really quickly. In our R4, foo recursing, we've hit a base case. We know as you've seen error stacks, it's literally the stack of functions that have been called. You would see something like, let's say, 3 argument can return that. It's very unpleasant to the eyes to look at. 6. Awesome. And then this is 10, and then 5 plus 10 is returned out or to us that we need to think about. Structures, curse things, do something else, right? Called pathing. You're going to really want to understand this. Is that recursion can actually be broken down, or the recurse step can actually be broken down into 3 steps, right? So the recurse thing can be into 3 steps. You have a pre, which means you can do something before you recurse. In our case, this was literally n plus, right? We took n and we added it, and then we did the recursion part. So this is kind of like our pre thing. Now, then we recurse, which actually does after recursing. So we didn't actually have to return here, right? We don't have to return. We could have said, hey, out equals this, then console logged something, and then returned out, right? Which would have actually, let's say we console logged, let's just say we, here, I'll just write the word log. If we would have logged out n, what we would have seen logged is 1, 2, 3, 4, 5. That makes sense because we did it post, meaning that as we recurse, we did the pre of adding, we went into foo4, we did the pre of adding, we went into foo3.
Oh, I didn't realize that. Let's try it right now. Wait a second. I was thinking he made a mistake. I was wrong, I guess. So we have DSA. Am I in the wrong section? No, I'm in the right one. So I will make a function, call it foo because that's the simplest number I can think of. Then I'm just going to do return n is equals to 1 and otherwise n plus 2 and minus 1. Okay, I just realized a mistake. If n is equals to 1, we are just going to return 1. If n is not equals to 1, then what do we do? That's a very nice question. Then we will return, then we will do const value is equals to n plus 2 bracket n minus 1, right? Then we will return the value, right? But in the middle, I will also like to console.log n. Let's see what happens if I run this. Oh, I forgot to actually run it. My apologies. It logged from 2345. That's very nice. Let's also console log this here. I will call it and terminate. So first of all, it logged 5402. Yes, perfect, perfect, perfect. So what is happening is, first of all, it will run the function for 5. It will check the index 1. We don't care. So it is 5 initially. It logged 5. Then it ran. Then it did this. Const value is equals to n plus. That is 5 plus. Then it ran the function. So it is again here. It will run the function again. Blah blah blah. Yeah, that makes sense.
When we went into foo2, we did 4 to the post of log 4. 4 return 5, 5 to the 5 log. A very valuable tool, a bit more clear, though you may not know how to use it. You can kind of hopefully see it a little bit clearer. We're going to rely a lot on recursion coming up here. And so that's why I wanted the algorithms on graphs possible. But, you know, it's hard. Anyway, so this was the simplest part of my lizard brain says, this is too simple, why not a for loop, right? Like I can't understand why you wouldn't use a for loop. I can't rock the need of it. I can't really see it. It just was really, really hard. So big mistake of recursion, solid base case, then recurse. Just remember that, please. It's so important. Holy cow. All right, so we're going to walk through the problem that truly helped me understand recursion. And this is actually a pathfinding algorithm on a graph. But don't worry, we're not going to do all that fancy stuff. We're going to break it into something that's really digestible and really easy to understand. So is everyone ready? Very, very excited? I'm very, very excited. Oh, I can't wait. Let's go back into here and let's create a new file. Let's zoom in twice because zooming in twice is the best type of zoom. And go up to the top. And so what we're going to call this thing is the maze solver. Oh man, that was just the worst E ever. Solver. Aren't you happy I don't have terrible handwriting? Imagine this classified terrible handwriting. I always thought like, oh man, because we had one professor that just, you couldn't tell if he's drawing an S or a 5. And you're like, is that a 5 or an S? And he would just never tell you, and he drew them from the same way. And someone finally asked in class, and it was very, very funny, and everyone knew what they're saying. Anyways, all right, so let's talk about a maze solver. So what we're going to have is we're going to have a list of strings. So you could imagine this, you could actually read this out from a file. We're not going to read it out from a file. Instead, we'll just have an array passed in. And this list of strings is going to contain some characters. The first thing it's going to contain are pound signs. It could be asterisks, it doesn't really matter. These are walls. You cannot go through a wall, right? Okay. This makes sense. Look at that, we already have the first row. We also have an ending, right? The ending, of course, is where we want to get to. This maze, very, very simple. And the third row, well, we're humans, there we go. Row we'll make really easy. I intentionally made this maze very, very simple. And the third row, we could have a start. Ooh. There we go. Oh, dude, you just go like that, man. It's just that simple. Well, you can't do that to a computer. You can't just go, well, look at that. Oh, I mean, maybe with DALL-E. I don't know. DALL-E, you say things to it, and out comes images that are crazy. So maybe you can do it these days, but for our sake, you can't do it. So how are we going to solve this?
First of all, we will do some looping to find the start. Then we will see if we can go left, right, blah, blah, blah. I don't know. You tell.
I'll tell you this much. Recursion is our friend. And I've never been asked this in an interview. I don't think this would be a great interview question. It'd be great to know that they know recursion, but that's about it. It's a very simple problem once you understand it. So first, how would we just theoretically solve this? Well, once we know where our start condition is, we know what walls look like, we know what pathways look like, and we know that we're looking for an ending thing. And maybe we're given the exact coordinate of the endpoint or just the, say, symbol it represents. It doesn't really matter what we're given. We just know that there's end, and we recognize that they're end. Well, what we could do, our human brain's probably taken over right now and say, okay, we'll go up. Well, again, computers, you can't just say go up, right? So what would we do? Well, at any one square, let's just draw this in more the abstract sense. What can we do at any one square? Well, we can go up. We can go right, bottom, left. And there you go. So we can do any of those four off the graph, right? Right. If we went down from start, we'd be literally off the graph. That would be really, really bad, correct?
Yes, sir.
Correct. We could also go to a spot we've seen before. That is pretty bad, right? You wouldn't want to just sit there and go back and forth between, maybe it's here, and then you're stuck forever in this loop because you didn't.
Yeah, that's right. That's right.
So we should consider these all our base case. And there's a good reason why you consider the base case and you don't check for it in the recursive case. It's very, very important not to do that. I keep stressing the base case because it just makes recursion a million times simpler. So let's think about our base cases. Base case. Well, one, it's a wall, right? If the point we're at in recursion, we are on a wall,
we
cannot be here, correct?
Yes, sir.
Right? You're on a wall. You cannot be here. So that's an invalid state. Perfect. Two. What's the next one? I feel like there's four. Now all of a sudden I'm confused. Oh yeah, off the map, right? If somehow you're in a spot that's not on the map, you have to return, correct?
Yes, sir.
That makes sense. Three, it's the end.
Congratulations.
If we make it to the end, we are done recursing, right? That is our actual goal, is to make it to that point, correct? Awesome. And then
I think we might even have 5 conditions.
If we have seen it. This part is very, very important. Have you seen this tile before? If you have, you also don't want to be here, right? We don't want to visit anything twice. So that's really the base cases. And then the recursive cases is simply checking every direction, is it not? So the recursive step is actually pretty simple. Just go all 4 directions. The base case is really, really simple. Can't be any of these places, and that's it. And so when you put these two things together, when we program them, it actually becomes very, very easy. All right,
Yeah,
so
that sounds good.
I believe at this point I said, hey, hopefully, let's implement it. Yeah, let's implement it. All right,
Okay.
So everyone ready to implement it? So in the kata machine, we can actually implement this. This is one of the things that I put in there. So if we go to our day 1 and go to maze solver, it is right here. So this is what we're passed in. We're passed in a maze, which is a list of strings. All right, so that's exactly like that, correct?
Yeah.
Awesome. We're passed in what a wall looks like. Hey, this is a wall. So and lastly, we need to return, I said lastly twice, most lastly, we need to return a list of points from the start to the end. Oh, this is where things get a little tricksy, right? Like this is where the hard things happen. Well, don't worry, it's not actually all that hard. So like any good recursive function, I often find that the entrance to the recursive function, like this function solve, isn't the one you want to recurse in.
Yeah, you need to make another function.
That way it just does. So let's just write a function up here, and let's call it walk, right? So we're just going to simply walk the maze. So remember, we want to be able to do our base cases, then our recursive cases. The base cases require us to know where we're currently at.
Yeah.
The recursive case requires us to be able to walk in directions.
Yeah.
So let's remember that. So I guess that means we probably need we need the maze to be able to walk, correct? Or we just need to know where we're at. We need to know the ending, because that, again, that's a part of our ability to know if we've been done. It's one of our base cases.
Yeah.
Just keep it like that. We're going to add some more things. Don't you just love when arguments get really long? I do too. And lastly, I am going to do this. I'm going to kind of give away part of the game. We're going to want to return a true or a false. And there's good reasons for it. So just let it happen. All right. So let's just start with the base cases. We don't even need to know how to do recursion to be able to program these base cases, right?
Yeah.
Base cases are pretty simple.
If
So let's start with number one.
current
Let's start with let's move these two around, right? Because if we're in a language in which you accessed outside of the bounds, it would throw an error. Right now we're in TypeScript, which doesn't do that, but we're going to pretend like it is because it's just good practice. So, one, base case.
So I will start
off
with
the map, right? So are we off
that
the map?
too, yeah.
So easy check. We
If
go current
current
x is greater than, or let's see, it's less than 0.
let me think. How do our maze exist? So maze is technically an array. Blah, blah, blah. So something like this is a maze, right? Let me just copy paste this. So this is our maze. So the length of the maze is equals to number of rows, and then the length of the row is the number of columns. So if I will do maze.length, that is the number of rows. And if I will do maze bracket 0.length, that is the number of columns. So x-axis, what does it represent? Most likely, let's think about it. So in a graph, we should use x for indexing to our column and y for indexing to our row, right? But it is our choice. It doesn't even matter. Am I dumb? I might be dumb, though, dude. So it cannot be less than 0, and current.x cannot be greater than or equals to maze.length. In this case, we will just return false. Of course, we can merge all the if cases, but who cares? Now the second case is if current.y is less than 0, or if current.y is greater than equals to maze bracket current.x. So if it is greater than the number of columns, yeah, simple as that. At the end, I will just do return true for now. So after this, our base case will be to check what? I forgot. So we need to make sure it is not a wall. So if I will do if maze bracket current.x bracket current.y is equals to the damn wall, that is not allowed. So we will return and return false. And after that, let's see what he does. Because if it is the end, then we should go on it. So it should be a true. But after that, we have to stop. So let's see.
Length, right? That's what we're grabbing out of here. Because remember, whenever you're doing 2D arrays, you actually traverse the columns, then the rows. It's backwards, unless if you draw it tilted 90 degrees. So, just fun little fact.
Let me think. So if x is equals to 0, it will go to 0, then it will go to that. My thing will also work. I will just do the changes that are required.
It just makes it easier because then you can print it in order. Now let's do another or, and let's do dot length, right? That's how many rows we have.
Yep.
There we go.
Yep. Well, his thing is a bit more better because in actuality, y index should represent the height based thing. I did something opposite and I don't really want to change it now.
Awesome.
So yeah.
So we have our first condition. Second one, let's find out code to actual code. Don't you a spot we're not supposed to be.
Yes, sir.
False. Our third condition equals n.y. Well, guess what? We're there. N.y actually sounds like a word. I don't know why that is. It almost sounds like endonym. Just kind of got my head there for a second. Anyway, so if we...
Okay, I guess I will add that as well. So if current.x is equals to n.x. Oh wait, the problem is if I am doing cases like this, his n will be opposite, blah blah blah, so I cannot do that. So dot x replace it to y, dot y replace it to dot x. It can, well, we can change it to y to be honest, but I am assuming that we're going to get a square matrix, so we can do 0 as well, but we don't care about that. So we will go to dot y, then dot x. So if x is equals to x and y is equals to n dot y, then that's a success. So we will return true.
But we do have on them, but then now we have this weird type that's both a point and put our base case. We're done. This is awesome. All right, but we do have one more condition, which is scene. How the heck do we do a scene, right? Well, we could mutate our points to have a true and false on them, but then now we have this weird type that's both a point and a Boolean, right? It's kind of weird. Maybe too much information on that single type. So what we can do, and one of the beautiful parts about recursion, is we can have a beautiful Boolean 2D array. Here's every position that is possible. False if we haven't seen it. True if we have seen it. All right, awesome. Look at that. Just made life easier. So if scene, current y, current x, then guess what? Return false. We don't want to be here. We don't want to keep recursing on places we've already been. That means you'd get into an infinite loop effectively. You'd blow your stack eventually. So you don't want to do that, because you could imagine even in this situation, if what we did is do, you could imagine a situation where you get down to order.
If we have seen it, then we return false. That's simple as that.
In CSS order,
Right? Sir.
You would get here, you go, can't go here, can't go here, can't go here, go back. Oh, I can traverse here. Can't go here, go this way. Oh,
that would
traverse
be
here,
bad.
here, go back. Oh, here, and you just and eventually you'd run out of memory and everything would explode. Because remember, we store return address, return value, and arguments. Therefore, you would run out of memory just calling it over and over again. That's what a Stack Overflow is.
Yeah.
In the easiest way. It's not the website in which you ask a question, someone berates you. It's actually what happens on a computer. It's named after something on a computer. It's different. All right, so there we go. We've done our base case. So now that we've done our base case, we can actually do the recursive step. But this was pretty easy, right? We can all agree the base case makes sense.
Yeah, it does. Totally. I mean, I can merge these two.
All right, so let's start the recursive case. Now remember, the recursive case is completely separated from the base case. You don't even need to think about what happens in the base case at this point. Now remember, I also said there's 3 steps to recursion inside the recurse case, right? There is the pre, there is the recurse, and there is the post, right? So the reason why pre and post becomes super important is because we're pathing. We need to go a direction and keep track of our path. And that also means our post is really important. Because remember, when you're recursing, you don't know what happens below your point, right? So let's just say we start, I'm just going to draw this more simple. Let's just say we get to here, right? We're 3 steps in. Well, we started here, and we started recursing in CSS order, right? That means we went to here. So before we went, we actually pushed into the array, hey, we're at start. Then we started recursing. So we first try going up. Then at up, we can recurse.
So it is pre.
Okay, I'm just going to call this, we'll just call that x naught. So then we get to x naught. And we say, hey, let's do CSS ordering. We go up, we hit a wall, we can't go there. We go here, and we go, okay, we can go here. We'll call this x1. And then we can push in x1. And you can see that we build this
It is
case
post.
in recursion. And as
I think it should be
unwind our
pre.
stuff, we'll actually
As
pop
soon as we enter, then we do.
That's why a pre and a post are so important during recursion. We do have a question.
What is CSS ordering?
Oh, CSS ordering. It's a joke. You know when you specify margin in CSS, margin is top, right, bottom, left. It's a joke. Maybe it's not that good. This reminded me of what my wife always tells me, that I'm not funny. This hurts a little bit, but yeah, that's how I remember things. So I just pick an ordering, and so often I'll just pick like CSS ordering as whenever I'm drawing something to do it in the order in which, right? Isn't that CSS? Doesn't CSS start at top? Yeah. Top, right, bottom, left?
Yep, it does.
Okay.
Chad says it was a good joke, so.
Thanks. See, that's why you guys get me. We get each other. All right, so there we go. So we're going to take advantage of these things, and we're going to build the path, right? Because we have to check all of our recursion steps, and then we can pop it off. So if we meet a dead end, we'll get to the dead end, check all of our directions, realize we can't go, then pop that last tile off our stack, then check all of our directions, finish checking our directions, pop it off, then pop it off, then pop it off. So we're building our path.
That's what.
All right, so let's start with the precondition. Precondition, ooh, we don't have a path, do we? Ooh, so again, let's just keep on adding, What's wrong with that? So we're gonna have a path, and let's have a point array. So every time we successfully visit a spot, we will add that in the precondition and remove it in the post condition. That makes sense because we don't know how much further we're going to recurse if we're going to meet a dead end. What's going to happen? Just something's going to happen. But at this point, we add, we recursion. If we come back out, we pop. So we can maintain this nice state. So one beautiful part about recursion and a stack is that it kind of maintains shape, right? In some sort of weird sense, it can maintain shape. So we go like this: pass dot push, current point, right? Awesome. And then for our ending, our post, we can just pop, right? So there we go. We push into our position, we recurse, we pop. Awesome. We're pretty much done. We've just built the path. Now all we need to do is curse. And so I'm going to give you guys like a sweet leet code tip. It's something that I've learned from a friend. I only know him by his internet moniker. Actually, I technically know him by his non-internet moniker, but it was Scooby-Doo. You can go like this: dir equals, and then you can put in 4 directions. And so I could go like, say, -1, 0, 1.
Oh, that is smart. Then we can just do plus x plus minus blah blah blah. Ooh, that's nice. I will like to copy that. That's beautiful.
Where are you? Where are you?
Directions.
And 0. There we go. So
That's the best difference I can do.
Those are our 4 directions we want to go. Right?
-1, 0. Then we can do
right, down,
left.
I just selected a random
right.
ordering. That's what we got. So those are the
Up,
differential
down.
directions, right? They're what we have to change to get to go that way. All right, so we can use that, and then we can go down to our recursive step. I'm going to have to use a for loop because we can't use sweet for eaches, plus they create stuff. All right.
Yeah.
I has to be less than dir.length plus I, and now all we need to do is recurse our 4 directions we want to go.
Alright, wait a second, guys. I will need to go somewhere for a minute. What is he making? So he is making a recursive function which will move through a maze and actually find the path to move. All right, I'm back. Yes, so Mike, that's what he's doing. All right, let's see.
So let's call ourselves again walk
Yeah.
with the maze.
Yeah.
And then right here, we need to have our new current. What is
So
our
we
new
can make
current?
it, I guess.
Well,
Square
our
is
new
equals to
current
x
needs
plus
to look
1
like this.
plus that.
xy equals dir I, right? So that's going to be our new current. And so let's go x, current x plus x.
Yes, sir.
Current
Y plus y.
plus y, right?
Yes,
we just
sir.
did a differential. We're going to go left, we're going to go right, we're going to go up, we're going to go down.
Okay.
It's a pretty simple, pretty nice little thing. A lot of times you'll see people like hand put in all the different calculations, all that. It can get pretty cumbersome. For me, this makes it a lot easier to understand, and I only have to specify it once right up here, which makes it pretty easy. Then you don't get all these pluses and minus ones all over the place, and then you're like, okay, which one did I do? Makes it a lot easier.
Yeah,
All
that's
right, what do we
for
have
sure.
left? We have our endpoint, we have our scene, and we have our path. Awesome. Now remember, I did return a true if we found the end. So if we do get a true and we found the end, we need to do something here as well.
Oh, my bad. But not this, but that. Wait a second.
Right? We can't just keep
Rock is path and Z. What do I actually need to do? I need to make current. Oh, it should be next. My bad. I thought you were making a Discord. No. I'm not making a Discord bot dashboard right now. Not right now, at least. Might make it someday. I mean, I will likely make one soon. I'm making a Discord bot as well, so I might need to make one soon. Anyways, let me do const response is equals to, I will need to walk again, and I will just give them the new current point. I mute myself by mistake.
Recursing once we found the end. So if walk is successful,
yeah,
we either return true, right? We just hit, this is kind of like a weird base case shift where you can't really do it. You have to stop your recursing. We have to stop it at this point, right? There we go. We've done it. It's great, right? Does this kind of make sense? Do you see how we're doing each check? We're checking in all 4 cardinal directions.
Let's see. So what are we actually doing? So first of all, I will start with running the walk function, and I will just do x0, y0. No, we will likely find the starting position, then we will do that. Let me just delete this as well. So let's say we found the starting position, we ran the walk function. Now, first of all, we are checking, are you out of the maze? Like, if the next step will take me out of the maze, then we are saying nope, walk cancelled. Then we are saying, are you on a wall? If yes, then this move is cancelled. Then we are saying, you found the end. True, congratulations. And in this case, we are going to end this walk loop. And then we will just finally return the path. Simple. Then we are saying, dude, you already tried this path, so ignore it. All right. And I just got a scam call from HDFC Bank impersonator, and it automatically got rejected, so that's very good to see. When will you start uploading about Discord JS 14? If you want, I recently made a video. It was like a live stream, but it was a video. Let me just show you content. So I made this video. I can make videos like this one. That's something doable. So pretty much I was supposed to open on YouTube, man. All right. So pretty much it will be a big video because it is non-edited, non-scripted. And people can give me a topic and I will just try to record it and raw upload it. So I can do something like that. That is, oh man, we have 48 views. I'm popular, shit. Anyways, wait, let's see. Yeah. So pretty much I can try something like that. But actually making a proper video like I used to do, I have lost quite a lot of skills. Like, let me think what skills I lost. Do I have any skill? Yeah. So first of all, I lost my ability to focus. Then I gained a skill called laziness. Then I upgraded that skill to tier S. So the stuff is happening, but I will try to make such quick videos, right? No editing, straight to the topic, unedited. I really don't want to mess something up. I don't know why people are only addicted to MongoDB for Discord bots. There are way more better DBs. Like, I mean, MongoDB is used a lot. Maybe that's why they use it, or maybe MongoDB is just easy. I mean, it is like MongoDB is a bit more available of a resource. Like, it is used by a lot of people, so it is easy to just find tutorials. Like this DB, I have never used it. It might be cool, it might be bad, it might be easy to use, it might be very hard to use. I don't know, man. So what is it? Introduction, blah blah blah, installation, macOS, Windows, run the Docker. So it sounds like we need to host it, probably. Install on Linux. Ooh. Deployment, yeah. So one thing about MongoDB is, if you don't want to deploy it, you can use their already deployed version. I don't know, man. It is easier to use it. I mean, this thing might be easy to implement. It is just we don't have enough tutorials. That's also a possibility. I will say that MongoDB is a bit more used, so it is a bit more easy to enter. But if I'm being honest, when I was not using MongoDB, when I was in the quick.db phase, at that time it was like too hard for me to use MongoDB. It was like I was just not able to use it. I don't really remember why I was unable to use it. Like, MongoDB is easy. Model.find one, blah blah blah. But yeah, it is, yeah, stuff. Like, when you are using QuickDB, it is too simple. You just do .set, you choose the key, you choose the value. But in MongoDB, it is a step harder. You initially make some schemas. In SQL, it is harder, relatively. Well, SQL is kind of similar, but it is more tabular than MongoDB. But yeah, stuff. People are addicted because it is easier. I don't know. Let's. Oh man, we have 5 likes. I think I'm actually getting popular now. I might need to start making proper videos.
And then we have a nice, simple base cases right here.
Yes, sir. We
the
do.
only thing, there's one bug in there right now.
What is it?
Does anyone notice what the bug is?
I don't know, man. Well, we are pushing to the path,
So let's
but we are not actually pushing the scene
start with the
value.
recursive case. Now,
Wait, by the it started from the start. Why?
which one did I do? Makes it a lot easier. All right, what do we have left? We have our endpoint. We have our if walk is successful.
Yeah. Let's skip all of this.
If we get a true when it's returned, it returns early, we get a true, which means the moment we get a true, we also stop recursing.
Yeah,
All
we do.
recursive stop recursing.
Yeah, that's true. QuickDB is not powerful as Mongo. I mean, yeah, QuickDB is kind of like using SQL easily on your desktop. I mean, on your machine. I mean, QuickDB is a very easy to enter starting point. Like, it is too easy. It is like using a set. Sorry, it is like using a map. You just do dot set. You can do dot delete. You can do dot get. So it is very easy to use. Like, it's way too easy, man. It should not be that easy, right? Well, we can also use MySQL in it. Like, we can use a host instead of a local file. That's nice. We also have a Mongo driver now. Okay, so I guess QuickDB have some improvements now. That's very cool to see. We have a JSON driver now. Okay. We have a memory driver. Okay. Okay, man. My apologies. You are good. But yeah, pretty much it's quite easy to use QuickDB. And it is a bit less easier to use MongoDB, but it is a bit better because we have more functions: update many, update one, delete many, drop the damn collection. By the way, your button videos for DJS proved not helpful. Oh, that's very good to know. Let me see how many button videos I have made. I think I made quite a few videos on those components and stuff. Let's see. So first of all, let's search for button. So, well, let's ignore the button bot full tutorial. Discord. Okay, so these are pretty much ads, these 3 videos. Then this is a real video. Well, yeah, buttons are quite cool, man. They deserve some videos for sure. I wonder if I made on select menu as well. I should have made few. Yeah, clickable select menu in 1 minute. What the fuck? Why is this video 1 minute? Does this even work? Let's find out what I did. So the video quality is perfect. Let me change it to something nice like 69 something. Advanced, you can download it via npm. So okay, Discord pagination advanced. Okay, sorry. I clicked on the wrong command. My bad. My apologies, human. So that was not actually a. Yeah, this is more like a 12-minute ad. I think you might have checked this out as. Oh wait, it is Discord JS 13. When did I uploaded this video? How do I check the time? Analytics, maybe. Analytics. So we have overview. Oh, 4.3K. Oh man, am I popular now? Okay, I think I can check the date here. All right, so I uploaded it on 7 Feb. I guess it's been quite some long time since I've uploaded. My bad, guys. Well, I hope I will upload better and more soon. मैं September 11 से okay, let's continue the video.
It says, hey, at this point our path array is completed.
Yeah.
Our ending tile does not get pushed in. So path push.
Okay. So we have to. Oh yeah, that makes sense.
And got to push in the very last one because it doesn't get added. So there we go. We should have a completed case. Long as I've done everything correctly, we should be.
So this should do the trick. Wow, that's crazy. I personally don't believe this will work, but let's find out. I will go to cd kata machine jest maze. Let's see. I don't have a good feeling about this. Let's see. I also have a good framework suggestion. It is about Sapphire framework. It's a really good alternative to Discord JS. More good than that. I have seen a lot of people using Sapphire for all sorts of things. but I have never used it myself, so I'm not very sure about it. I mean, 2014, I think that's the wrong one. Let's check this one out. Sapphire Community, a pleasant Discord bot framework. Okay. So it is a Discord which is built on top of DJS for advanced bots. Ooh. Okay, so we need Discord just installed. Okay, sir. Okay, sir. We can buy some donuts for these guys. Totally, we should. And let's view some code. Oh, we can also click here for documentation. Okay. By the way, how do we actually make those buttons inside the README file? What? How do I do that? Let's start by stealing some README code. Where is the README? Where is README? README.md. And I want to see the raw stuff. Let's see. Support server. Oh, legit HTML. Oh, we can do HTML. I didn't knew that. My apologies, humans. My apologies. That's quite nice. Anyways, let's start with stealing some. Let's look at the docs. Discord. Let's go to documentation. Let's go to guide. Guide will be easier to see. So we can get started. You need Node.js 18. Okay, sir. We need 2 dependencies. Okay, sir. If you want to use enable. What? Why? If you intend properly to include these intents, load messes in your. Oh, if you want to use messes commands. Okay, I was like, why am I required to do this if I don't need it? My bad. I think I'm not just what should I say? Okay, let's see. So we have to make an index.js file. I can do Sapphire client. Okay. We can also set a default prefix. Blah blah blah. Then we can create a basic command. Let's see how that works. So we have a plugin sub command. We have a plugin for sub commands. Nice. Okay, load message command listener. Okay. So we can import the command. We can make the constructor context command.context. Let's ignore all of that. So we first of all need to add this thing so we can enable the message create event. Okay, then what do? Message run have message in it. Then we do stuff and we do the reply. Message.edit. Oh, we already sent this. Okay. Resulting code. Then we have Sapphire plugin for subcommands. Sapphire plugin for subcommand. We need Sapphire utilities. I guess we can use these things for sure. Subcommand name, subcommand type. I think we have a lot more things done already, a lot more abstraction. Totally tryable, I guess. Do people want to watch that? Let's find out. I remember there was something called YouTube tag searcher thing or something. Like I can just ask them if this particular text is doing good or bad. Wait, why do I have that many views? Am I popular now? I guess I am. Yeah, research. Yeah, there it is. So let's try to find out. Discord Sapphire. I don't really know how to spell Sapphire. Let's search. Search volume is medium. There is no content gap. That's interesting. Let's just search Sapphire framework. Nobody searches that. That's my bad, I guess. Sapphire JS. Sapphire bot. Sapphire Discord bot. Well, it do have some medium searches. Okay, that's interesting. Okay. Who cares? In Sapphire, we don't need to make a command handler. Framework itself handles everything. So we just do interaction command handler true and then it will do it. I think I did make something on a smaller scale really long ago. I made something like that. Let's see. Discord / command and sync.io. What is that? Package health is dead. Popularity is dead. Maintenance is dead. Community is dead. Okay, this package is dead. That's what they are saying. Okay. Let's open it on NPM instead. Let's see. Okay, I published it 1 year ago. So I think it works with Discord JS 13. We still have 57 downloads. What? People still use it? Why? All right. Let's see. So yeah, it was something similar. Users can, but it doesn't have the client class. You can use it from this. Wait, it have its own client. My bad. My bad. I think I should have included the handler inside the client itself. Then it would have been better. Yeah, it only supports version 13. Okay. So we do new handler. This is bullshit. Then we pass the options like command folder, command type. I could have made it better for sure. This is not good enough. And handle argument for / commands, how to define a command. So it is pretty much something. I made this thing when the / commands were new. So it was not very easy to add them at that time. But now that package is kind of bullshit and ancient, so it's
be able to go here.
dead. Anyways, let's see how the test went. So there is only one path through. What does that mean, son? What does that mean? What does that mean?
And actually do it.
It should not actually work, to be honest.
We didn't get it because, of course, we forgot just
to return.
All right, so let's script. We didn't need our path, which is going to be our point array.
Yeah, he didn't run the functions. Okay, let's see. We have scene and we have path. Amazing.
All right. We also need the dot push new array. Let's go for let I equal 0. I has to be less than
maze.length. Yes, sir.
Scene dot push new array
of maze.length.
0 length. Oh no. Oh no.
All right, let me just write all of those things myself as well. So first of all, we need a for loop that goes to till every y index in the maze. Then first of all, in the scene section, I will just push an empty array that will be equals to maze bracket I dot length. After that, we need to just walk.
Fill false, right? There we go. So we've now
we can fill as well. My bad. I mean, if you don't fill anything, it is fine because nothing is kind of like false.
Technically, this is JavaScript. We didn't have to do this, right? If you would have accessed something outside of your bounds, it would have been undefined. And
yeah.
It's technically false, and we could have just turned them to true as we saw them, and that would
yes, sir. Then we need to walk.
And walk takes in maze, while start is our current position we want to start at. We want to get to the end, and then if I'm not mistaken, let's see. If I'm not mistaken, I'm pressing all the wrong buttons. We have to have scene and path, and then we can just return out path. So if we've successfully done this, we will return out a completed path. If it gets to the end,
you didn't define the start. Oh wait, we have the start. Oh, I was thinking I will need to find the start myself, but start already exists. Why am I so dumb? How can a human be that dumb? I really want to know that. Please tell me, my human friends. How am I so dumb? Anyways, let's see what's up. Let's see what my... Where is he? Where is he? There.
More bug I just thought of in my head that I forgot to do.
Yes, sir.
Part of the pre, we always need to go scene.
Yeah, that's what I was saying initially. I think I should use my mind instead of trying to just copy his code. Because I'm kind of copying his code, to be honest. Right? So we will do current bracket these things. Sorry, scene bracket these things is also true.
Catch it before we try, we wouldn't have been able to get a first try, which would have been very, very sad. All right, so we rerun this one more time.
It should not work.
Now we have another one right here on line 8. Classic oopsie daisy saying, hey, there's a boolean, and apparently we forgot a case to return. Did I forget? Oh.
You didn't return true at the end. Is that the case?
If we recurse and we reach the end and we did not find n.
Oh, then we didn't false. Ah, it should be false.
You know, I feel like we got a compile error there.
Well, it passed, but it shouldn't have passed, to be honest. But
of course, it's
that's
first
good
try,
to know.
of course. Absolutely. So there we go. We got it. Fantastic. For those that are wondering what we just solved, if we go to maze solver in the test, here's the maze that we just got done solving. And this top point right here is our start. I believe this is our end. And we build that exact path.
All right, let's console log some things.
So
let's see
right?
what was the path.
To do that. And then this is kind of the out we expect. So we were able to solve that. Hopefully this makes recursion either more clear or you feel more confused than ever. But I'm hoping that it makes it more clear in the sense that always think about your base case. It honestly is going to save you so much headache if you can do a clear and defined reason why you should stop recursing. Often what I'll see is in the recursive step, people will try to test for it. Like, oh, is the thing I'm about to go to null? No, don't do it there. Put it in the base case. Makes it a lot easier. Is the thing off the grid? No, don't do it there. Put it in the base case. Move everything you can into the base case. Your complexity will go massively down, and it's a lot easier to solve. So hopefully that all makes sense. A common question you get is, when do I use recursion, right? Because a lot of these things seem like we can do a for loop. Obviously, the last thing we just got done doing is clear you can't do a for loop with. Well, I mean, you can if you use the stack and you kept track of your own state and all that, but you wouldn't do that. That'd be crazy talk. So that's my general rule of thumb, is when I can't.
All right, so the path is 10, 0, 10, 1. I think I should open that array as well to actually understand the path. How do I do that? I will need to find it. Maze solver, amazing. So initially we are at 10, 0, x 10, y 0. So we are here. That y is 0. I guess we are initially here at 10th index. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yeah. So initially we are here. Then we are still on 10. Then we are here. Nice. Then we are at 2 and it is still 10. Nice. So we are here. And after that we are at 3. Nice. After that we go at 4. After that we are just decreasing the number x by 1 till we reach here. So after that the bot might have went here, then 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 here. So yeah, that's also a possibility. We might need to add some better casing for that. Let's actually do something. All right, what if I make this thing impossible? Like, what if it is just not possible to do it? What if we have an x here as well? Let's see what happens in that case, right? I just wanted to console log the result. Let's see what happens. I want to see what will be the path. Like, the path should be empty. It should have the start point only, right? Let's see what will happen. I really wonder what will happen. Stuff is happening. So it was successful. Okay, I think I will just keep the x there. Clear 1, 2, 3, and let's see how it will go this time. And meanwhile, let's continue the video as well.
Concretely use a for loop, meaning there is no defined end, especially if there's a branching factor. You can imagine that the maze that we were just doing had a branching factor, right? You could do 4 possible directions at any one point.
Okay. Hit a wall. That should not happen. Cannot read property of undefined, reading 0. That should not actually happen. So can you show me again? Maze bracket current of y. So y cannot be something like that. That's not real. This is unreal. Let's go to maze solver and then let's try to find the issue. So if y is less than 0, it should be or y is greater than this. Then we have current x is less than 0. Or, dude, what is wrong with my if conditions? Am I dumb? I think I am. My apologies, humans. This time I will not get that error. I will that test will still fail, but it will fail in a successful way. I will let you know if it fails successfully or if it fails not successfully. So the console log is expect received equals to expected minus 6 received plus 6. There is only one path through. Can you please show me the damn console log? Console log is empty. That's exactly what I expected, kind of. Anyways, let's go to the solver. Where is it? Where is it? Because we don't really have a path, we cannot move, so it should be an error. All right, now if I remove this x and if I put it right there, this time we will have x10 y1. Anyways, meanwhile, let's go here.
Grid. Therefore, the branching factor is 4. So how do you do a for loop for that? You can't just write a for loop simply for that. And so that's my general rule of thumb, is how do I avoid using recursion? If there is a terminus, something I can see, and it's a simple for loop can do it, always use a for loop. Else recursion. If you write your recursion correctly, it becomes aggressively simple. You write it with base cases within your recurse step, it becomes aggressively complicated.
That is still that.
Any questions from chat? Anyone have any questions? Now's your time. Great time to ask questions.
Kind of on the maze front, if like we have the seam, so if we're going some way and then like we have to go back, like, does it get mad that it's going back on its own path?
So that is a good question. So in a sense, yes, and in a sense, no. So the question, of course, was we walk a certain direction in the graph, but then at some point we can't keep on walking, right? So we have to undo, but then we also programmed in that you can't go back on your own self, right? Well, let me
in the post condition, we are kind of in those things, I guess.
So when we're doing the maze solving, let's just say we have these two things, right? We have x0 and x1. So we're at x0 and everything's great. So our path is to x0 right now. Our scene is now true. This one's false, right? That's kind of the state of the world we're at right now. Well, then we check up. We can't go up, so we don't go up. It returns false right away. Then we go over. We can go over and we start recursing. So we put in x1, right? Oh, that was a terrible x. Do you see how sad that x was? Here you go. x1. Perfect. We put in x1, and then we start recursing. And this becomes true. Awesome. We go here, it's a wall. We go here, it's a wall. We go here, it's a wall. Then we try to go here. What happens?
It needs to
Scenery,
go back,
right?
but it is
Scenery.
seen.
Oh,
So it is false.
We can't go there. So then what happens?
It have no more conditions, so it will return false. So we
get done
go back.
recursing. We pop the thing off the stack, and then we return back the function, the return address.
Yeah. So if we don't find the next move, we cancel the current move and then we go back. I guess that's what it
Then
means.
it gets popped back to the previous one that was called, which we were called from x0. So we pop this off the stack, and then the function returns to here, and we check downwards. Because remember, we're going top, over, we recursed in top, over, down, this way, return, down, over. And algorithms there for a second, it was beautiful. That was like a really weird 90s reference that just came to my brain.
Big thing in the test case, how did we end up in that output? Like,
how would you end up in the top?
No, the output, the test case, if we look at the test for this, yeah. So the start is...
We are giving the start index, my boy.
And is x is equal to 1, y is equal to 5, right?
Yeah.
So how did we end up in that output? It's still a little bit confusing for me.
How did we end up in the top function?
No, the output.
How did we get this?
Yes.
All right, so let's go back to this simple case, because I think this simple case really helps kind of see it. Is that I'll redraw it, and we'll just only talk about pathing, right? So yes, this order. So we land right here, right? Let's just say we start right here, one away, and now we push it into our array, and now we recurse. We try. Let's see. Let's go with not yellow. Yellow would be very hard to see. Is there anywhere, right? So then we try to go into, for this one, where now we do it again. At this point, our scene array now becomes all trues, and now we put in x2. x2, of course, attempts to go up, It cannot go there. Attempts to go this way, cannot go there. Attempts to go this way, cannot go there. And then it attempts to go this way, and it fails because of that true, right? So then we're done. Now this whole function returns, and it returns a false. But before it returns, it pops from the stack. So then this one does the same thing. Checks down now, checks over, see an array, fails, pops from the stack, returns. This one now checks down, finds the end, pushes the end into the stack, and then returns completely.
Nice.
And so now we have now built this array as we walked. Push, 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 pop, pop, push. We do have one more question.
Is there any scenario where the order would make any performance difference, such as going top, right, bottom, left?
There is no difference in the general case, right? If we could inspect or look at, then yeah, in some sense we could automatically guess, because right here, if we go down and then left, then up, then right, obviously it would effectively walk straight to the exit, right? But if we tried up first, it'd go up, couldn't go. Then let's say it went this direction, couldn't go. Then it eventually get to here, try to go back, oopsies, it tried to go up again, couldn't go. This one couldn't go. Then let's say it goes this direction. Repeat the same thing, can't go, can't go, can't go, can't go. Oh, don't go down. Then go over, can't go, blah, 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 all the way till it gets here. And then what's it gonna do? Run up into here, and then run up over here. It's gonna go explore that whole space. Since you don't know the graph ahead of time, you can't really seed it with a direction that would make most sense. So in the general case, absolutely. In this specific case, we know exactly what would get there in the shortest possible path. So you can't cheat the system, in other words. Got that, kids? All right. This really is your chance. It's recursion. It's just really fundamental to these next parts.
Okay, let's think about recursion once more. What do we do? In the base function, we have our inputs. We take our arguments, we take our output variables, blah, blah, blah. Then we will actually have the recursive function. In the recursive function, we actually get the arguments. Now, first of all, in the recursive function, we have base conditions. Base conditions are pretty much like, do we need to end this recursion? So these are the base conditions, so we end it. Now, after that, we have to do a precondition. Preconditions means do something before doing this recursion. So we do something before doing that recursion. Then we actually do the recursion. For recursion, we will just do something that will lead to actually running this function once more. That is recursion. And then we have a condition which is called post condition, in which we do something if the recursion is done, after recursion is done, right? Now we also need to think about this. We can sometimes break inside a recursion, then we don't have the post condition at all. So I guess that is called the recursive condition, I believe. Let's watch it.
All right.
What would be the big O time for this then?
Well, the big O time, though, this is where things get kind of fun. We can think of this as, let's just think of it in a different kind of sense.
I mean, it sounds sense where
we don't have to solve it for the whole thing. Let's just solve it for a specific, specific square. So, ooh, I love this blue color, don't you guys? It's beautiful. All right, so we have this square, right? And really, it has 4 possible entrances into the square, correct? So that means we have the potential from this side, whatever the perimeter is, minus all the inner sides, right? Besides for all that kind of complexity, what you'll see is you'll see at max 4 checks for every square in the graph. So if we use S as our notation, then it'd be big O 4S, drop that, it's effectively linear, right? For every point, we would just call big O of N, right? And so that's as slow or fast as you can get.
It's linear.
Walls you only
Or
check
number of
once, right? You can really, I mean, I guess technically, if there was an island wall, you could get all 4 checks on it. But if it's some sort of perimeter wall or walls adjacent, that amount of checks go down. And so, there you go.
Yeah.
Radical, huh? All right, let me go back to black on this, because if I don't, the next time I create something, it'll be very blue, and we'll all go.
Okay.
I had a joke about a vampire there. We let it go though. So now we're actually to the end of the array list section. Actually, for real, this is it. We're going to do one last algorithm, and that's it. So hopefully we all feel pretty dang good about this. Remember, you may have forgotten, but I said we're going to do 2 sorts, right?
Bubble and quick.
Do bubble sort? No, we're doing it. We're doing it. And 2, quick sort. Quick sort is a fantastic algorithm. It's shockingly simple, and at the same time, it's like shockingly brilliant how someone could come up with this. To me, it just blows my mind. I don't think I could come up with it by myself, but whoever did it, maybe the constraints of having a really slow CPU would have made me come up with this, but I just didn't have that problem, right? I've been born in the gigahertz days, right? Kind of makes you forget how great things are. There's actually an algorithm technique known as divide and conquer. So normally in algorithms book, often you'll see merge sort as the one they use, but this one we're going to use quick sort because I wanted to be different. You can go read about someone else's merge sort. That way you have more breadth of things people will explain. So what is divide and conquer? Effectively, divide and conquering is to be able to split your input into 2 chunks, 3 chunks, 4 chunks, whatever the splitting is, and then be able to go over those smaller subsets and solve things faster. Then you could resplit it again, and resplit it again, and resplit it again.
Kind of like
it becomes something in which
binary search.
It gets smaller and smaller until it gets to some sort of fundamental unit in which you can solve really easily. So think about sorting. An array of 1 element is always sorted.
Yeah.
So that would be like, say, the fundamental unit in merge sort is once you get down to that point, your array is sorted. Now we need to just do the undo function, which involves merging, hence the name, merge sort. All right. There are a bunch of different algorithm strategies. I didn't technically really name any of the algorithm strategies as we go. There's greedy. So linear search is a greedy search. We go until we find the first one, we're done. There's also dynamic programming. Dynamic programming is one of those things that until you really get it, it's really, really hard. And for whatever reason, almost every single company asks you the same. If you had a stock chart, what is the best day to invest in? Which is just a dynamic programming problem. Oh, it's very annoying. All right, so first we're going to go over quicksort algorithm. It really is a super fun algorithm. Yeah, by far one of my most favorite ones. I think I get to program. I have a fun story about it, which I'll go over here in a little bit. But for now, let's just talk quicksort. All right. Do you like that? Do you like that? We could even use quicksort. All right. So quicksort works in such a way that it divides and it conquers. So let's just pretend that we pick some element out of the array. It doesn't really matter what the element is. We're just going to call it P in the array. We pick the last item, and then what we do is we have an index that hangs out over here, and we walk our entire array. So then we have a second one that's going to walk our entire array. Any element that is less than or equal to our pivot will be put in the first little runner's position, right? So we have that first pointer that just starts at the beginning, a second one that just walks the array. Every time we find one that's smaller than our pivot, we put it in that first position, increment our first runner. So we're putting all the ones that are smaller than or equal to our pivot on one side of the array, then our pivot, then all the ones that are bigger than it on the other side. So starting to kind of look like sort. You can already see a sorted item in here. So eventually what we should see is that our first pivot should be somewhere in the middle-ish, right? Who knows where it's going to be. And everything on this side is going to be less than or equal to. Everything on this side should be greater than. This is referred to as a weak sort at this point. You'll see other data structures tomorrow that actually take advantage of an idea called weak sort to make super fast operations. And so it's actually pretty cool. And then at this point, we need to split our problem in twain. Yes, twain. We are going to take the positions betwixt the pivot and the ending, and betwixt the other side of the pivot and the beginning. And we repeat the process again. Pick another pivot. We'll call this one pivot 1. Eventually pivot 1 will be, but we include everything around the pivot. And we just keep on doing their always sort side. So it becomes progressively more sorted at this point. Progressively more sorted at this point. So let's kind of think of it in a different sense.
So pretty much every element which is our pivot or which we choose will be in the center. And then we will go through both of the sides, left and right, and there we will choose a pivot and we will set that thing in the center and then blah blah blah.
Draw it in a different way this really, and I'm going to have my high can make things, and we do it again, and it's going to be from 17. What is the middle element here? 24? That seems to make sense. I'll just keep on going down this one. It's in this through, and eventually when we're at this bottom part, all of those pieces are sorted.
So we will just merge them all.
We're done sorting. We have them all. And so again, what we're seeing here is that we're seeing a way that we break the problem down more and more to the point where everything eventually becomes sorted. Obviously,
that's interesting. Give me a second, guys. I am back. Humans. I feel so light. Anyways, let me just hide my screen for a second. I need to do a Google search. Wait a second. Holy fuck, man. Something bad happened. Can't help it. All right.
Everything this direction is less than or equal to, which this direction is less than or equal to, right? It walks back up to this whole quicksort business. again, this is why we did recursion before we did this step. It's because you can see right away we have this branching factor within how we're solving. The branching factor is, of course, 2. We have 2 branches every single time we execute quicksort. And something else at this level, we had to go over still all of the input, right? Save this one little pivot. Then we went over all of the input again, save this one little, the couple.
So it is n raised to power n?
We keep having to scan the entire input every single time until we get down to the very bottomest level, which means that
is fair.
N operations
N number of times.
all the way down to when n equals 1, which of
Then
course is
might
our
be n
beautiful
squared.
equation of n equals 2k equals 1. Remember that? Do we all remember what n equals? Log n.
Yes, sir,
There
Lord.
we go, which means our running time for doing this is going to be log n.
Okay.
N log n. We scan n times, we do an n log of n. Hold on. We do a log n amount of n's. Yeah, there we go. And I knew it eventually would come out of me eventually. It'd get there. But is that true? Is that true? Is that what's going to happen?
If you say so.
Does anyone see any problems with how I kind of described this?
I'm thinking, like, what if you don't get in the middle?
Boom! That is exactly it. Quicksort doesn't always sort quickly. I know. It's a very deceiving name. You never know what you're going to get out of this one. So, can anyone think of a condition based on how I've described the algorithm which will actually produce the worst possible answer?
If we have the greatest value, probably.
I'll let you go back up and I'll show you how I did it.
If we every time choose the greatest value.
Making it a little bit easier.
If you start at the beginning.
Yeah, if we were right there. Yeah, so oh my, perfect. It's ridiculous. A reverse sorted array, right? If you are handed an array that goes 10, 9, 8, blah, 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 down to 1, and I pick this number, what happens to our pivot?
It will take
our
it to
pivot
the
will stay
left.
like this. 1,
And then everything
hanging
else.
out there by itself. Because remember, we put everything on this side of the array that is smaller or equal to it, and then we put, goes over, goes over, goes over. It goes all the way up for n amount of scans, n minus 1 amount of scans, n minus 2 amount of scans. What's the run to? Fantastic. We have now just done that, which of course breaks down into the classic n squared over 2 plus n over 2, which drop all the constants and lower order stuff, and all we get left is that right there. So that's what happens. So quicksort is not just simply n log n. It can also be n squared, which totally sucks. That's not what you want. And so there are some strategies. One of the big strategies is always pick the middle element. If it's reverse sorted, you should get perfect bisecting. If it's sorted, you should get 0 swaps. If
It's not sorted, then can help.
if it's just completely random, you'll have a random chance of being somewhere nearest the middle, right? I think over time, you'll probably fall within a certain middle region more often than the fringes. I'm pretty sure everything usually always ends up being a normally distributed function, but you'll get somewhere in this n log front of merge sort is. And so quicksort is often the one that is reached for, that does really, really well, but it can have poor performance if you just hit all the right conditions. Again, the chances of you hitting all the right conditions all the way through to get n squared is exceptionally low, I would assume. So it's somewhere between n log n best case, n squared worst case, somewhere in betwixt there. So pretty fun one, huh? It's kind of an interesting one. It's one that you can't. And I think that's all we have to do with it, except other than the fact that I'm going to tell you this really cool story. All right, so this real cool story is that I was on a team that was the first team to be a non-MIT student team to make it to MIT's finalist in MIT Battlecode. So Battlecode is where you program these little computer robots. They're like simulation robots, and they have to battle it out. And you have to do all this different type of fighting. There's macro, it's like imagine StarCraft, right? It's like StarCraft, but for people that aren't smart. And so it's like really, really simple, and there's very few conditions. There's no races. It's just like people in a base often. And there's every single year, it's a little bit different. Sometimes there are races, sometimes there aren't, blah, blah, blah. It's pretty cool. And when we were doing this, I had this thing where if a certain resource was between us and our opponent, then I'd want to capture that and turn it into a turret, right? So if they tried to come near us, we'd be able to shoot them really easily. Super, super easy. They couldn't get us. It was a way to just dominate them, right? And so I thought, okay, this is what we're going to do. I could take all of these different resources that are on the map and I can just simply sort it and find which ones we need to do certain different things with. It should be really, really simple, right? Well, of course, the constraint with MIT Battlecode is that you only get 10,000 bytecode operations. This is in Java. Everyone loves Java, which means you actually get very few things you can do any one turn per person. So I couldn't quick sort it. Within like 5 elements, the guy would come out of the base and then just sit there for like 20 frames and just be dead in the water. And then as the base got more of them, sometimes they would just stop, and then our whole thing would stop, and then we'd just die. We're like, what is going on here? And it came down to the sorting algorithm. You couldn't simply sort because you'd run out of time. You'd run out of computation that's available per turn. And so what I realized is that if you look at this thing, what you're going to see here is that this is just a tree, right? This is just a tree filled with states. And so if you really think about it, you don't have to do this recursively. You just simply need to know where you start, where you end, process that thing, and it may produce 2 children. If it produces 2 children, add it to a stack. And then you can actually get the exact same thing. And so that's all I did was every single turn, I'd go, hey, how many do I have left? Which there was a function to say how much computation you had left. And if I was like, hey, if it's below 1,000, then don't do any more sorting. Go do your other things so you can like move around. You can see if there's bad guys near. You can do other operations without running out of space. And so it became this kind of like simple way to avoid running out of space. So these things do become useful. Obviously, that is an obvious case in which is so specific you'll probably never run into it. But nonetheless, it is something to always, that's kind of fun to think about, that you can use these algorithms in really unique ways that actually become super useful. And I'm sure that taught me something that I've used throughout my life. I want to end on a positive note somewhere, right? It was great. All right, we got 13th, which means we lost in the finals right away. All right, so we went over the running time, somewhere of n log n all the way up to n squared, depending, right? And of course, next we're going to implement quicksort. Hey, did you know that I teach a course on Vim? This sweet editor that I'm using that's super fast and super cool and goes really, really, really fast and all these great things. Yes. So if you're ever curious, I do a developer productivity, which allows for sweet this and Vim usage and all the great stuff. Fantastic. Okay. Anyways, back to it. You have to sell your own course, It's just a part of things. All right. So let's do quicksort. So this is the test for quicksort. I have a debugger here because obviously I've gotten it wrong multiple times in my life. So this is the array we're going to sort, and hopefully we can sort this. So let's just jump to it, and now it's the sorting time. So we get an array, and we're expected to sort. So there's 2 functions that we really need to think about. If we replay what I talked about, there was this whole like
get into the middle,
running these 2 things side,
then
right?
we need to go left
But
and
there's
right.
also this whole pivoting side. So often when you see quicksort, it's split into 2 functions. There is something referred to as the partition. I think that's how you spell it, which actually produces the pivot index and moves the items that are less than or equal to on one side and the items that are greater to on the other side. Then the second thing is your actual quicksort, which does the quick sorting, which calls partition, gets the pivot, then recalls quicksort, does the recursive
Okay.
step I'm going to call quicksort, right? So I'm just going to call it QS, quicksort, make it easy, pass in the array, and then we need to pass in the low and the high.
That
So
will
the
be
high,
Q
remember,
auto
what did I
transform.
say specifically about the high? I think I said it right on the screen too.
2 to even 1 medium.
Right there. It's inclusive. A very unusual thing you do in most algorithms. You don't do that. So let's do r.length minus 1. Minus a smiley face. Minus 1. There we go. So now we just need to program 2 functions.
Alright. I guess I can just make a function and I can just call it quicksort. I can just give something like row and hide because we string it as well, might need the array as well. Then here I need to do something like return with sort 0 from array to length minus 1 array. Now here, first of all, I need to do partition. How do I do that? I have no damn idea. So think about it. First of all, we might need to do something like if array.length is equals to 1, then we just return the array. I think that should be the base case. After that, we need to do partition const left comma right is, I mean, this is a way to do it, but we can do it in different ways as well. Function partition. I personally don't know how to spell that myself. I will do partition bracket arr. Now, by the way, this should be a number. It can be a index, or it can be an array of number. Let me copy that for my boy. Put it right there. This thing can return an array. Something about that. Now, how do I actually do the partition? We need to pivot and then center left and right. Okay, left and right. Okay.
The quicksort function, again, the recursion function, and then the partition function, how we get the index. So just to make, if we really wanted to, we could just return back out the array to make it super simple. We don't have to do that. You can do that. This one doesn't actually need the array right here, so we don't need to do that.
Oh.
Void, awesome. So we have that one done, and then we need one more. We need the function partition, right?
Yeah.
All these little spots in here, right? It needs to be able to run, you know, on 1 through 7. So we need to be able to give it, hey, you're running from low.
Why is this for slash command in DMs? I use client.application.commands.set. Because if you will use global commands, that command is global. That means it exists every possible where. So if you wanted to only exist in a guild, then you set it per guild. That is painful. So you can just make a if condition. If the command is not used in a guild, say something like you cannot use this command in DMs. And if for checking that, you can do something like if not interaction.guild. Then return
7, right? We have to be able to do all these things. So we have that right here, and it needs to return back out. What is the pivot index? Where did we end up splitting the array to? Where did we weakly sort this array?
Oh, so we don't really give the left and right, huh?
So which one do we want to start with? Should we start with quicksort, or should we start with the partition?
We should start with the partition, I will say.
Partition.
I love that. Someone had an opinion.
Yes.
All right, so let's start with the partition. So the partition shouldn't be too hard. We'll just do the easy way, which is I'm going to create a pivot, which is going to be simply the array at the high position. I know this could cause that whole sorting, reverse sorting, super duper issue, but let's just have an easy time with this. We don't need to do anything super fancy. Then at this point, I'm going to create an index. This is where, so most books will actually create it at -1. You'll see why they do it in a specific.
Give me a second, my human friends.
यार तुम्हारा वो वाला फोन स्विच ऑफ हो गया मैं तुम्हें बहुत देर से कॉल कर रहा हूँ जी 1 सेकेंड वो आ जाओ तो बात
All right, so I really hope I didn't give away a lot of information. Let me delete my WhatsApp real quick. Oh, I have to close it, not delete it, my bad. Let me show you the screen once more. I might just mute. All right. Give me a second, man. I think I might need to do a call and stuff. Give me a second. I mean, it might take me a while, so I should probably just end the stream. I got it. All right, I will be back soon. Hopefully, see you.
Alright, guys, I am back once more. Oh, by the way, I was dying. Let me fix that. Dun, dun, dun. How do I fix that? Oh, it is reviving itself. Alright, I don't know. Oh, alright. So where was I? I was watching Quicksort. Yeah.
Specific way. You don't have to do it this way. You'll
Okay.
see most pseudocode. I'm pretty sure if I went to Wikipedia right now, it would actually say that. Start at -1. So at this point, we need to walk from the low to the high, but not including the high, because the high is the pivot. So we just have to now do a weak sort on this subarray. So let's do the weak sort now. So for let I equals low, I has to be less than high, plus I. Now, what are we comparing it to? Remember, each element needs to be compared to the pivot. Not like I plus 1, not something adjacent to the pivot. So if array I is less than or equal to the pivot, we now need to put that value into the first slot or the second slot or the third slot or however many slots we need to put it into to make this into a weakly sorted array. So we'll go like this. Const temp equals array I. Oh, forgot this. So in the most pseudocode, you'll find that they first increment the index at this point. That is now, we're now into the 0th position. We went from -1 to the 0th position, which I've also done something wrong here. We got to go to low -1, right? Because we have to be able to put it into, where is this?
Oh,
we
yeah.
have to be able to also, we need to be able to put stuff into the 9th position or into the,
Yeah, whatever.
Position. Remember, because we're doing these little subsorts on these different spots within the array. Always forget to do that. That's one of the ones that got me multiple times. That's why that debugger message was there. Forgot to put or take advantage of using low. So low -1. So right now we're off of it. The moment we find something we need to swap, we move it into the first position. Now we do the flop. We're going to go array I is now going to need to be swapped with array index or array I equals array index equals, what is it? Temp? There we go. Swapping, I don't know why it's always so hard. I always mess it up. It's just the worst. So there we go. It's as simple as that. We've now...
Wait a second. I have way too many of these. So AR bracket I should be equal to the AR bracket index. Then AR bracket I wait a second. Then AR bracket index should be equal to the temporary, right? So we are taking the current element, we are replacing it with the pivot thing. We are putting it to the left, and then we are taking the left element and we are replacing it with the current element.
Found everything and moved it over into the beginning of the array that is less than our pivot. But we have one problem left. What is the one problem left?
Well, if the index is equals to -1, I don't know.
Let's see if we can do this. Here, I'll do this. So I really want this one to sink in. I feel like Quicksort's just such a great algorithm. I just really want to make sure that people really get this one, which is, let's just say we had an array of 1, 7, 6. I didn't plan on doing this, so hopefully this all works out swell-like. And let's get it. And we start off with index that's here. No, it's not. Is this less than 5? It is less than 5. So let's
we will put it in the 0.
Here. Is that the 5th one? Oh, it also happens to be the 5th one, or the index 4 right there. So there we go. We've now flopped it. Last thing we have to do, we have to put our pivot
in the middle
where the pivot index is, right? So that way we hold true to the one rule, which is everything to the left of the pivot needs to be less than or equal to, and everything right of it needs to be greater than it. So we're going to have to do one last swap right here. So let's go back down here, and we go index ++, increment it once more,
All right. Mic testing 1, 2, 3, 4, 5, 6, 7, 8. I'm back. So what we are supposed to do? We are supposed to do some changes once more. So I will call it the pivot index, and then I will also define it as that. So technically, I'm just replacing this. I'm replacing the pivot index element with whatever the new or actual pivot index we find. I hope doing. I really hope so.
So if we found nothing less than us, we'd increment it into a position of 0 or low at this point. So we do that.
Yeah,
and now we're going to go array high equals array index, and array index equals pivot. We already have the temporary specified right up there, right? So I didn't need to create the temporary variable in the swap. There we go.
Oh, that's very true, man. How can a human be that dumb? Why? Why am I that dumb? Anyways, who cares?
And the last thing we need to do, of course, is
return the
index. Right here. Fantastic. We've done it. We've written the pivot algorithm. Was that kind of hard? Was that a lot to take in?
Yeah, I'm dead.
Hopefully these explanations, these things make it a little bit easier to kind of walk through and follow this, which is fantastic. All right. So let's go up to quicksort. So now we just need to do the quicksort side of things. So what's our base case? Well, when we get to the point where low and high meet, right? So that is a bad time. If low equals or is greater than or equal to high, I always put greater than, even though I don't think that can ever happen. It just makes me feel
safe.
Like I just catch all the possible conditions. I don't know why I do that. It just feels good. You know what I mean? So once this happens, we have now officially stopped needing to recurse. We've ended the line, which is going to be partition, and we need to pass in the array, the low, and the high, right? So this thing is going to do the weak sort. It's going to set the pivot into the correct spot, then return the pivot's index. So now we need to just repeat this again,
until
make sure we don't include the pivot index on our repeat. So quicksort array low to pivot index minus 1, right? Because remember, it's inclusive endings, not exclusive endings. So if we didn't have that right,
and then we do plus 1 comma high.
To make it all work out, we'd have to put plus 1s and minus 1s elsewhere, so we don't have to do that. Oh, we do have a question?
Why use 5 as a pivot?
Oh, in this case, all I did was pick the last element. So I wanted to make it identical to the algorithm that I did, which I just simply pick the last element. I didn't pick 5 as a good choice. I just picked it as the choice I programmed. All right. Then, of course, remember, we need to go. We're going to repeat the quicks over and under going right now. But do we feel like I've gotten this first?
I don't feel so.
Okay. We have just people are out there saying absolutely. All right. Quicksort. So we're going to run this, and I get this one. Ah, look at that. We got it. There we go. So we got.
That was fast. Certainly. Let's see if I got it. I mean, I literally copy pasted score, so of course I got it. But of course I added the middle thing instead of the left, right, instead of choosing the last one. So I might have messed it up. So we have a lot of undefineds. We have a lot of undefineds. Interesting. So let's think about it. How can we have a freaking undefined? That's a good question. Pivot index is equals to that. I guess I will just do high minus 1 like him. I wonder. I really wonder. Okay, I will just do high. My bad. It feels so sad, man. It is less than high. This is depressing. Then we no longer need this condition because that will never happen. Blah 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 blah. Let's run it again. What did I mess up in the middle? I wonder about that. Anyways, let's see.
All right, quicksort. So we're gonna run this, and I get this one. Ah, look at that. We got it. There we go. So we got that first try. I just knew it.
Okay, I guess we have something wrong here. Let's see. So we are doing quick sort. We are sorting the damn thing. That's fine. That's perfect. And then what are we doing? So first of all, low and high is that. You see if low is greater than or equal to high, then we just stop. Otherwise, what we are doing is we are getting the pivot index. And according to that, we are running the quick sort again and again for the left side and for the right side. That's perfect. Now let's actually see the partition, if that is right or wrong. So in the partition, what we are getting is we are getting the pivot index, that is the high. Then we are getting the pivot value, that is whatever is there. Then we are getting the current index, that is low minus 1. That's perfect. So then we are looping from, we should not loop from 0. We should loop from index, I believe. Right? That's the problem, right? Yeah, that's the problem. Wait. Loop since low. Oh. And it should be less than high. Yeah, that's nice. Because otherwise it will loop from 0, then it will mess up the other things. Even though it is not supposed to mess up the other things. Okay, let me restart it. And this better work this time. If it doesn't, I cannot do anything about it. If it works, then I will try the middle thing. All right. I have a good feeling it will work, but I have a bad feeling it will not work. So let's see. So the good feeling won. That's very good to know. It's always good to know that the good feeling won. Now I will like to change some if conditions. All right. Now I will change it to low. Beautiful. And let's try it once more with the middle. Let's see how that goes. Very omoshiro. Meanwhile, let's watch this video.
Okay, we have just people are out there saying absolutely complete confidence there for a second. So there we go. So that is all quicksort is.
The middle doesn't work. The middle doesn't work. May I know why? Should I just try that? If it will not go to the high, that's not really nice because I'm not including the high, so we need that. Anyways, I guess we'll need to think. I don't really want to think. I'm too dumb for it. So I will just change it to high, smooth, and from now on it will work because I know it will.
It's just a simple partitioning and repeat.
Oh, that worked. That's good to know. That's very good to know. Wait a second. So if I did change the high thing, it worked. So I can actually, this thing works. So this is right. We can take the middle index and then we can do the looping. Because even if it is equal to the middle index, then we're saying no. I think we will also need this condition. Okay, so let's restart. So blah blah. Okay, let's see if that works.
This is a divide and conquer strategy. I find this one to be really awesome. Easy. It's much easier to program than merge sort.
Merge sort
often used is very complicated in my book. So I like this one.
Yeah, I found merge sort quite complicated myself.
At that point,
but this thing is also complicated for me, so no comments.
We did it. We're kind of done with lists. There's no more lists.
Okay, let's try to remove that.
We're going to be done. We're fully done. But technically, in a sense, lists are actually
everywhere.
Trees, in some sense, they're kind of like, they're very similar. So we're not really done. We're just kind of done, right? You're going to have a whole load of node-like opportunities coming up. And we're going to use a ton of recursion. So if you're not familiar or if you felt like your recursion chops weren't quite up to snuff, you might want to take a moment. And so all programming eventually leads to trees. This is just a fact of life. The Falcor thing that I mentioned where I could have ruined all of Netflix, that's just a tree. Well, it was actually a forest, which is a series of trees that were also pointing to other trees. It was like a graph that was also a set of trees. It was very confusing. I can't quite tell what it was. It was a linked list and a tree and the graph all at the same time. Just depends on how you looked at it.
Okay, sounds very complicated. And I guess for now we are sticking with the high.
Time to implement the linked list. So let's actually implement it. I'm going to adhere to this interface right here. And so we are going to actually do all of these. Some of them are a bit trickier. I actually did take the Java interface. I know no one likes Java anymore. It's not that cool to like Java. But hey, Netflix uses a lot of Java. So it is cool to like Java. That's what I told myself as we did this. So let's go over here. Let's go to our kata machine and let's open up linked list. If you wish to join in, we'll be doing a doubly linked list because they are doubly a singly. It's true. Mathematically checks out. No one can argue that. All right. So I actually nicely have everything kind of generated for you right here. I believe I know I did at one point implement this right here, this Git. So I'm just gonna if you like money. I like just so that way we implement it continuously. You know what I mean?
I just want to say Java is cool if you like money.
Java is cool if you like money. I like money. You like money too? We should be friends, you know? That is a shout out, of course, to everyone's favorite movie, Idiocracy. So there we go. So often whenever I'm doing a constructor, I like to explicitly set things. So let's do head undefined.
Yeah.
We don't actually need to do this. So now if you remember when it comes to linked lists, all right, so to be able to do prepending, you may remember the operations. Let's jump back over to our diagram right here, and let's just kind of walk through just one more time. So prepending does involve the head, in which we're going to need to be able to set in a new node at the head's position, which means, let's just call it G. And what we're going to want to do is we're going to want G to point to A first. Then we're going to want A to point to G. Then we're going to want the head to point to G. We're going to kind of want to do these in this operation. We don't want to lose.
I will keep the tail with me because then the append thing becomes easier.
A in our memory.
Otherwise, I will need to loop and find the last element and then do the thing. It's same, but yeah.
We don't want to lose any of these things. We want to keep these operations in order as much as possible. So let's do that right now. So if we're going to prepend something, we can start off by first creating the node, right? The node, of course, is going to be a value item, no head, right? There's nothing here. We don't have anything. We can just set this as the head, right? We don't need to do anything fantastic. So this dot head equals node. Perfect.
Yes,
and
sir.
How do that? Bookkeeping. See, let's do those exact steps again.
Oh, I forgot to do the bookkeeping. I'm so bad. My apologies. This.lamp plus plus, if we are inserting plus plus, if we are appending plus plus, easy. If we are removing minus minus, of course we will need a if check for if not this dot index or this dot head, then we can just return undefined. Of course, we can do the same here as well.
Remember, G points to A points to G, head points to G.
Yes.
So let's do those three ones. So let's go like this. Node next points to our head. Or in this case, it was A in that case, right?
Node
This dot head dot previous points to node.
next to the head,
So we've done
and this dot head dot previous to the child, and then the head is child.
two directions. Now, this dot head.
This goes to the child. Yep. Perfect.
We have now just official linked list. Insert at is the exact same thing except for
But we
now,
need to find the node.
within the middle. We'll be doing the F operation right here. So let's rewrite it out and as the we have which means we all add we can't really insert at that point, can we?
Nope.
So what would be a good move here? I would probably
Either
just throw
we-
here, right?
Yeah, we can do that, or we can just edit at the end.
No, right? You can't really do it at this point. I don't know what else to do, right? You're two nodes off. Should we create two dummy nodes with no values in them? No, we're probably going to screw that up. It's going to make our logic a lot more complex. Probably the right move to do. Well, there's actually something else that makes this a little bit interesting. What happens if our index is the length? Well, we're really just appending to the list, right?
Yeah.
We can technically just call append, right?
That's true.
Right? Yeah. Why not? What if our index is 0? Well,
Then we are just
we're just really just
yeah.
just prepending it, right?
Yeah, totally.
We've already written those two. All right, fantastic. We don't really have to concern ourselves with the edge.
Alright, man. I will go sleep now. Can't hear you properly. You are not audible at all. My bad. I think I should need to figure out a way to actually be more audible. I can decrease this probably and actually learn and something at the same time. But for today, that's it. Gotta go and eat and see you all tomorrow. And thanks a lot for joining the stream.